আরেকটু নিচে করুন। এই আরেকটু।
হ্যাঁ ঠিক আছে,
ঠিক আছে, ঠিক আছে।
হ্যাঁ একদম পারফেক্ট।
ডক্টর উৎপল রায়, হ্যাঁ উনি এসে গেছেন। হ্যাঁ এবার বোধহয় ছবিটা তুলে দেওয়া যাবে।
উৎপল বাবু একটু অন করে প্লিজ।
করেছেন তোমার উপরেই আছে।
Engineer, start the program.
নাকি নয়েজ আসছে?
ক্র্যাকিং সাউন্ড আসে।
তাহলে আমি ম্যাডামের পারমিশন নিয়ে আমি স্টার্ট করছি। তাহলে গুড আফটারনুন এভরিওয়ান। Good afternoon, Principal Ma'am and our speaker, Dr. Utpal Roy, and all the respected participants and students. I welcome you all to this one-day webinar on quantum optics and in quantum information, its fundamentals, and now before we start with the actual lecture, I will request our Principal Madam, Dr. Nivedita Chakraborty, to deliver the welcome address to us.
Thank you, Gayatri. Good afternoon, everybody. Respected speaker, Dr. Utpal Roy, Associate Professor and Head, IIT Patna, and all my teacher colleagues from VIC, Victoria Institution College, and from other colleges, and my dear students. On behalf of Victoria Institution College and on my behalf, I welcome you all to this national webinar. I would like to thank first the resource person of today's webinar to accept our invitation for giving a talk on quantum optics and quantum information from basic to application. I'm very sure about it that this will help our students very much. I appreciate the coordinators and the physics department for Victoria Institution College for organizing national webinar in this tough time. We are passing through an unusual situation due to COVID-19 pandemic. Even with a high technological advancement in 21st century, still, world is facing a severe crisis. In such trying time, when social distancing is necessary in this new normal for survival, the webinar like this uses the time efficiently. Our college is an old heritage college established in the year 1932 for female education to make them independent through education. I think which is still relevant for our society. Here I would like to point out that those are very, you see, we have female scientists very less number in comparison to male scientists in India. So we should always encourage the girl students to choose research as their career. And you know, if we consider our college, we see that the number of students, just comparison I'm telling, that the number of students in the arts department and the number of students in the science honors department, see, honors department students of the science are very less. And from that to the higher studies, lesser number of students go for higher studies. So we another thing I would like to point out that economists are now considering knowledge as an important factor for making wealth of a nation. So we should encourage our girl students and the boys also to choose the research as their career also. And because, we are not using our half of the workforce for the development of the nation. As women are not involving, too many women are not involving in the research. You see that in CSIR, in ICMR, the very, very less number of scientists are there. So we will expect this type of webinar will encourage the students to think, to go for the research or higher studies, or to take their profession as a scientist. Now coming to the topic, today's topic of the webinar, I can say that I am also a student, a learner today. I will learn so many things I expect from our speaker today. And just one thing I must say, that application of quantum optics and informations are highly challenging research areas in recent time, which expedites the implementation of quantum technology in various practical systems. And you see, I think I can say that application, we need basic research, and application is very, very important. So I think this is very important for the student, for the researcher, for other teachers also. So I'm very eager to hear from Dr. Roy with our students also. And I hope this will help our students. And once again, I would like to thank our speaker, today's speaker, Dr. Roy, and everybody, all the teachers and my students, and welcome them to this webinar. Okay, thank you very much.
Thank you, Principal Ma'am, for your encouraging speech. Now I will request the co-convener of the joint convener of this webinar, Dr. Shubhendra Chandra, to deliver the introductory speech.
Thank you, Gayatri. Good afternoon, all of you. On behalf of the Department of Physics, Victoria Institution College, Kolkata, I express gratitude to Dr. Nivedita Chakraborty, Principal, Victoria Institution College, for consenting to be chief patron of this national webinar. It is my great pleasure to introduce Dr. Utpal Roy, Associate Professor and former Head, Department of Physics, Central Vigilance Officer, Indian Institute of Technology, Patna, Bihar, as resource person of this one-day national webinar on quantum optics and quantum information from basics to applications. It is worth mentioning that without huge support of outstanding technical capabilities of Dr. Sinjini Dasgupta, the convener, and our departmental colleague, this webinar could not have been arranged. I convey my heartfelt thanks to all the teaching and non-teaching staff of the Department of Physics for their cooperation and hearty support. I also welcome all the teachers and students of various colleges, institutions, and universities for their participation. We feel very happy to arrange this webinar on quantum optics and quantum information, which will able to develop our knowledge. I think the students and faculty members of basic sciences like physics, chemistry, and various streams of physical, chemical, and biological engineering will be benefited through enrichment of their knowledge by attending this national webinar under the able guidance of the respected speaker. I feel honored to organize this webinar despite pandemic situation all over the world. I hope all of you are well, stay home and gather energy to fight against COVID-19. Once again, I express my gratitude to all of you. Thank you. So, we now come to end of the inaugural session of the one-day national webinar on quantum optics and quantum information from basics to applications. At the end of the inaugural session, again I make my gratitude to all of you. Before going to the technical session, I would like to request to mute your audios and off your videos for smooth running of the webinar. Any questions arises from the participants must make their questions through chat. All the questions are valuable for us. Chat box is always open for the participants. We collect the questions from the chat box and convey the questions to the speakers. At the end of each session, the questions will be discussed. The lecture are of two parts. The first part of the webinar will have to pedagogical approach, thinking of the benefit of the young audience. Fundamental concepts of quantum optics and quantum information required to understand feasible applications will be elaborated. The idea of macroscopic quantum matter will be covered in addition. In lecture 2, it deals with the applications towards couple of novel quantum phenomena will be presented in continuation. Recent progress in quantum simulation and quantum sensing will also be emphasized. Now, we are going to start the technical session of the webinar. The speaker is Dr. Utpal Roy. Dr. Roy is an associate professor and former head Department of Physics, Central Vigilance Officer, IIT Patna. His area of research deals with Bose-Einstein's condensation and quantum information, quantum simulation, quantum sensing. So now I would like to request Dr. Roy to start his presentation. Dr. Roy.
Yeah, thank you. So first of all, I would like to extend. Am I audible?
Yes, sir.
So I think it is, there's some echo somewhere. I'm listening my own sound.
Now, sir, you can try again.
Yeah, I think this is fine now.
Yeah, right.
Okay,
Right,
good.
you are okay now.
Okay, so first of all, I would like to extend my sincere thanks to Dr. Nivedita Chakraborty, Principal, Victoria Institution, for giving such a motivating and warm welcome address. And thanks to Dr. Shubhendu Chandra for very elaborate introduction for the webinar. And definitely, I am thankful to the Victoria Institution and the whole Department of Physics, especially Dr. Sinjini Dasgupta for inviting me and to present my, I can say, work or deliver my lecture today. So, which is very important is, I can see very large number of students, registered participants, and it is really appreciable that to arrange such event to get them acquainted with academic environment in this pandemic time, and especially for the girl students, like Principal Ma'am mentioned, that we have to work together in our society. So the society has to be kind of modulated, not the girls. So to take them ahead of the things. So I'll try to meet the goal through my lecture. And so let me first share my screen so that I can go to the lecture. Yeah, so is my slide visible now?
Yet not yet, sir. First choose your slide, then yeah, present now. You are doing it from the computer?
Yeah, I'm doing it from laptop.
Your
I hope
laptop?
it should come now. It should come now.
Yeah, it is coming.
Uh,
It's visible now.
yeah.
If
So
it's possible, if yes, it is.
is it fine?
Yes, sir.
Okay. So pardon me if I'm going to a very basic level sometimes, which is obvious to many of you, and because I have included a kind of a reasonable part of my talk for students as well, and in addition, I have included some applications to kind of we are actually going through a quantum revolution, second quantum revolution rather, and where understanding quantum world is becoming essential even for the people who does not deal with quantum mechanics. So because the technologies are coming hugely about with quantum world, so this is very important. And then I'll mention about the physical systems for which the technological implementation is possible. So this is about lecture 1, and lecture 2 is mostly of ultra cold atoms, Bose, Einstein, Condensed, is because I'll focus on the system which are very much useful in current technological aspect. So one of them is ultra cold atoms or Bose, Einstein, Condensed. So that's my second lecture. So first lecture, because I said that we are going through a second quantum revolution, and almost all the developed countries and developing countries, they have invested their maximum R&D fund towards quantum technology. So and the reason is that and you have to also understand that the quantum world is something which you don't see in our bare eyes and daily life, and implementation is also not very easy. So why a difficult thing which is not by default visible to people, and people are investing the maximum amount of money and effort and the manpower as well. So why so is because it is unavoidable. So you cannot avoid quantum world. So I'll try to convince you with the things. First of all, the discovery of quantum physics is still going on. It is continuous. So I have included one slide for students, just giving some discrete names. You can see that there are only names, and I normally used to ask if it is a lecture in a hall or a lecture room. I used to ask the students, do you know some of these names? Probably some of them know about some of the names. And then what about these names? Yes, they are the Nobel laureates in quantum physics. So I have included up to 2015, but in 2017, there are Nobel Prize for gravitational wave detection is a very remarkable steps towards quantum interferometry. So there are more works, but if you look at it, all the steps, it is not the developing the field that from the time of Schrodinger and Born and Planck, it was discovered, and then nothing, it is discovered completely. It is not. It is continuously being discovered. At the same time, technology is also being implemented. So I'll mention in my talk some of the some connections with some of the Nobel Prizes. For example, 2012 by Harrows and Wineland, that I'll be mentioning. Then there are more than 65 Nobel Prizes somewhere related to quantum physics. So these are the underlying things which I'm going to mention: R.J. Glover, Cornell, Italy, Wyman, and then Chu, Tanucci, and Philip. So yeah, so these are all Nobel laureates since beginning. So it is just to tell you that the subject is so vast and the discoveries are continuously happening. The theory is continuously being developed, and when someone develops the theory, it involves a lot of steps, like some prediction, some laws, some theorem, and then verifications through experimentation. and then it goes on a loop. So predictions, experimentation, sometimes experimentation, then invent the theory. So this loop is still going on since beginning. Now this is the second motivation. It is famously is very famous in the area of quantum computation. Moore's law. Okay, this is available in Wikipedia, and this says that these dots are, you can see the x-axis, which are years to 1970 to 2016, and it says that every 2 years the transistors, number of transistors in an IC doubles. So that means that you are able to say, I consider that I have a laptop with a given specification and given size, then the company will be able to manufacture another laptop of the same size but double of the efficiency in 2 years. Okay, so that was the situation from beginning. So it was the electronic world, although it was the first quantum revolutions, like we see the transistors, ICs, those are all fundamental idea is the quantum mechanics. But you don't have to apply quantum physics theory from outside in the circuit itself. So that's why it is not difficult to implement the thing. So we have all the electronic circuits that can be kind of modified to make it more and more efficient. But imagine a situation that you are trying to miniaturize the circuits and getting it more and more efficient, but you can go up to which extent? That's the point. So you are actually going to a very small scales, and you're going inside the matter, you are fabricating the ICs and all, so that is going to a kind of micrometer, then nanometers and so on, and then you are actually supposed to reach to a atomic level. So that you can see in the market, whatever laptops, whatever electronic gadget is coming, the efficiency is not kind of a doubling up. They are just changing one thing down and another thing up, a little bit variations, and some improvement in some aspects, but not of the speed of the circuit and the efficiency. So that's the point where there is a saturation. But if you want to go ahead with more apps, more modified operating systems and programs, then you have to modify your own circuits. So there comes the quantum computation. You have to implement everything through quantum gates. So this is a sudden jump, just like a drastic jump you have to have, changing everything from classical to quantum. But that is why from the year 2000 itself, the people have been trying all over the world to implement things, quantum circuits, quantum chip, and so on. And there are products in the market nowadays. People are Toshiba, IBM, Google, and they are selling a lot of equipments, which is quantum equipments. Okay, now what is the appropriate starting point? The starting point I have chosen is classical harmonic oscillator. Okay, and this I don't have to explain because everybody understands. If there is a spring, it will oscillate around an equilibrium position, right? And so the question is, why classical harmonic oscillator? Because this is the system which appears the most in real life. Okay, whenever you try to explain something, some system, some phenomena, probably classical harmonic oscillator appears the most compared to other models. So equivalently, you can expect that you should have a quantum version of it to go ahead with quantum world, right? So that is why people have started with a quantum harmonic oscillator, and students know about this formalism of writing the Hamiltonian of harmonic oscillator. The expression is not same, is a different. Why? Because there is a cap over x, there is a cap over p, and these two are operators. So normally when we write quantum mechanical expressions, the observables which you can measure are represented by operators, Hermitian operators. So you can take x and p, both are operators. But then what happens that you take some drastic mathematical step, okay, out of nothing. So you intuitively understand, okay, probably I can try to factorize the Hamiltonian, by some two operators, because Hamiltonian is itself an operator. So you try to factorize. Say, can I write H as a multiplication of A and A dagger, where A and A dagger both are conjugate to each other? The answer is no, you cannot write. But at the most, what you can do is H is A dagger A plus half H cat omega. Okay, and also one can check that this A dagger minus A dagger A is 1. So this is actually called the commutator, but I have not used those terms here. This is a very famous algebra called Heisenberg-Weil algebra. And this is the properties of the system. So if a system be consistent with this model, then that system has to have the symmetry which is consistent to this algebra. Okay, but apart from that, this Hamiltonian can be written in this fashion. But so far it is completely mathematical approach. So A dagger does not give us a physical meaning till this slide. So let us check that what is it. So next thing, that I define another operator which is A dagger A, and because it appears here, so we write it in terms of a single operator which is n plus half H cat omega. Okay, and then try to examine what is A. So if you apply this A on this wave function, then apply the Hamiltonian on that, what you are going to get is E minus H cat omega, and then the same state. So that means this function A psi is the eigenstate of the Hamiltonian with eigenenergy E minus H cat omega. So that means it is reducing the energy by H cat omega. Why it is reducing? Because you are applying the operator A. And that is why it is called the lowering operator. It is lowering the energy by 1 unit. Why 1 unit? Because this is known from Planck's black body radiation and Planck's theory that, you know, the minimum amount of energy, one single amount of packet of energy is h nu or H cat omega. So it is a lowering operator. Now what is the annihilation stands for? Is standing for, because if you are going for a higher state to lower state, one step lower, then there will be emission of one photon. And this photon is lost by the system. So there will be emission of one photon, the photon will be lost. So that means it is annihilating one photon from the system. So this is also called annihilation operator. Okay. And similarly, you can see that this A dagger is also raising operator. That means is raising the energy by 1 unit, H cat omega. At the same time, it is also creating or generating one photon. Why so? Because if one photon is absorbed, then the particle or the atom or whatever can go from a lower state to a higher state. So that's the idea. So you get to know about the meaning of A and A dagger, which is actually possible when you write the Hamiltonian. And now you can build up a basis now. So when you are working with an operator and then write the Hamiltonian in this fashion, you did not know what was n. We defined n as A dagger A. Now if you operate using all these informations, you are going to get n plus half H cat omega. So you are actually having this number in place of this A dagger A, you are going to get a number. So that is why it is a number state. It's a number state. Okay, this state n, which is the eigen function of this operator, is called the number state. And so the number states can be built up by operating A dagger. As I said, A dagger will take you from 0 to 1. If you apply another A dagger, it will go from 1 to 2 and so on. And then if you apply n times, so you are actually going to get n. So 0 to n. So this is the eigenstate and eigenvalues. So eigenstate is n, eigenvalues, which is En. Okay. And the question arises, how do they look like? And for that, you have to know what is the expression in the coordinate space. And it is known to the students that we can solve this, the ground state wave function, this. But then what is important here is look at the expression And I'll request to remember this expression that it is a Gaussian. It is a Gaussian, e to the power minus some constant 2x square. Now, if you compare with the standard expression of a Gaussian, which is exponential minus x square by 2 sigma square. So what is sigma? Sigma is the width of the Gaussian, right? So what will be the in place of sigma, which is square root of h cut over m omega. And this quantity, square root of h cut over m omega, is a very important entity in physics. And you must have seen in many places, length is scaled by square root of h cut over m omega. And it is because this is called the harmonic oscillator length. So this is the width of the wave function of the ground state of harmonic oscillator. Okay, I will tell you another analogy of this quantity h cut over omega, square root of that, later when we come to a wave packet concept. So like that, you can have the expression of the higher eigenstates. Now, let me visualize these states, eigenstates. I'm still looking at the eigenstates here. Now, this red ball, this is the picture which is taken from Wikipedia again. If you give a search in the Google that quantum harmonic oscillator, the first thing what you get in Google is the Wikipedia link. And you go there, and there it shows that how the eigen functions, if you look at C, D, E, F, 4 pictures, and these are all eigen functions. C, you can see, is a ground state wave function. This is the first order, like n equals to 1. This is n equals to 2, n equals to 3. These 4 figures. Why there are 2? Because it is you cannot plot wave function. Why? Because this is a complex quantity. Wave function in general is a complex quantity. So you can at the most plot the real and imaginary part. But remember, wave function is a completely mathematical approach. Okay, but it can describe the whole quantum system. So the real part and imaginary part is given by blue and pink color respectively. And the bottom 2 things are the superposition. Like if you superpose C plus D plus E plus F, then it goes to G. I'm not talking about H because I have not discussed about the thing which is done in H so far. So that's not required for the timing. Now, let me look at it in this representation. In phase space. In phase space, you know that this is a space where you visualize a state or the wave function in position as well as in momentum. Okay. So this is a ground state, n equals to 0, you can see, and this is for n equals to 2. Now, the important point is that one coordinate is x, another coordinate is p, and what is there in the z-axis? So what is there in the vertical axis? In other words, what you are plotting in vertical axis. The origin of the question is that the wave function is a function of position. Wave function can be a function of time, but it cannot be a function of both x and p simultaneously, right? So you can definitely make a Fourier transform and go to a momentum space, and then you get the wave function as a function of momentum, right? So it is definitely not the wave function which you are plotting here. So what is it then? So that's the natural question to ask. Now this is nothing but Wigner representation. Is a unique representation, and everybody is using this representation when representing a quantum state in phase space. Okay, and I'm not getting into the mathematical expressions. As you can see that the wave function, if you know psi, you know, and then you can actually build up the Wigner function, which is a function of x and p both. Okay, and that's the thing we require. So if you want to plot something in the phase space, you need a function which is both as a function of x as well as p, right? So this wxp is the one which you are supposed to plot in phase space. That's called Wigner distribution. Okay, now some very important properties of Wigner distribution here. So if you integrate this function with respect to momentum, you get a probability density of position. Okay, because you have to anyway correlate to a observable entity, which is probability density in the first place. Now, if you integrate over x, you are going to get the probability density in momentum space. Okay. And most importantly, I've given the red, color for this word. I have given hyphen, but there's no hyphen. But because I'm using this word first time, so that one can kind of see both the things together. So negative region signifies negative region of what? Negative region of the Wigner functions. If you have a negative region, when you plot the Wigner function, Wigner distribution, this function WXP, if you see any negative region, if the function goes to negative, then you can understand the system is quantum. The more negative you get more quantumness. Okay, so that's the very, very important characteristics of this distribution or this representation. Okay, and there is of course this overlap thing which is written here. That is a kind of a starting point of the field, which is called quantum metrology. So how precisely one can measure something, measure one parameter, say position, how precisely you can measure, momentum, how precisely you can measure, or maybe time, how precisely you can measure. That's called the quantum metrology. In classical metrology, we have been dealing with such things, but then there is a limit in classical metrology, and it has been seen that in the quantum world, your precision is much more higher. And that's why the field quantum metrology has evolved, and this relation is very important, the last one. So what is the take home from this slide is we have to use Wigner representation that I'll be using in many places, and that's why I have introduced this function. That's not a wave function, it is Wigner distribution, and it gives you the quantumness as well as it gives you the starting point of quantum metrology. Now, if you look at the wave function once again, that now we are plotting a Wigner quasi-probability distribution. Why it is quasi-probability is because if you integrate one quadrature, you are getting the probability in another quadrature. Okay, so that is why it is quasi-probability. It is not probability, but some operation on that can give you the probability. And here is a plot for n equals to 0, n equals to 1, and n equals to 5. I'm not going to explain in details, but this n, even if I don't write it here, you can understand from here by the number of zeros. So it goes to the negative region, definitely, because it is a wave function of the quantum harmonic oscillator, and then it is cutting somewhere inside, and that's the zeros. And if you count the number of zeros, that will be equal to the Eigen function, quantum number. Okay. So now the question is, in the fundamental quantum physics book, students always solve a Schrodinger equation to find out the wave function, then plot it for infinite square well, a step well, potential barrier, harmonic oscillator, and so on, right? And hydrogen atom and so on. Quantum tunneling. So everywhere you see the plot, which is wave function. So how is the wave function? Now this particle concept is also mentioned, but not in a major way in the quantum physics textbook. And you can represent a particle in quantum physics by wave packet. Okay. And why is so? Because what is a property? What is the property of a particle in the real world? The particle is supposed to be very localized. You can actually see that where it is moving. So you can identify the position. You can identify what is the speed and so on. So you can, first of all, it should be very well localized. Okay. And it should not decay. Say you cannot define a particle which is here and it is no more after 10 meters. So that's not a good particle. So it is something else is happening over there. But a particle has to be having the same shape while moving. At the same time, it should be very well localized. And that two properties are maintained through the formation of the wave packet. That is there in the beginning of the quantum physics approach. Okay. Now this wave packet, what kind of wave packet? We have many kind of wave packets. So all of them are appropriate description of a particle. The answer is somewhat no, because this is the starting point that Schrodinger in 1926 has come up with a very remarkable idea, that there is something called non-decaying wave packet of quantum harmonic oscillator. Okay, so I have written down here non-spreading wave packet of harmonic oscillator. Now, if you can build up a wave packet which is non-spreading, then it is an ideal description of a particle in quantum physics. Okay, although the name was not given coherent state, that was given later, but this is a starting point where we get an idea that there has to be some state which is very coherent, it does not decay, and very localized as per the Schrodinger. So then comes the contribution like the Nobel Prize 2005 by R.J. Glover, our ECG Sudarshan from India. He also kind of contributed immensely in this direction. Both of them, Glover and Sudarshan, you could have heard the name together. Glover got the Nobel Prize in 2005. Sudarshan did not. And his contribution was that in 1963, there was a back-to-back papers on quantum coherency. So very beautifully, he has explained what is the meaning of coherence. So the coherent word is so broad and, kind of having a lot of debates about this coherence. But then he first time kind of illuminated this field by his seminal papers on quantum coherence. So how much, if you say that is a coherent superposition, naturally question arises after that, how much coherent, how long it will remain coherent, and so on. Okay, so how to construct a coherent state? So how to construct a state which will remain coherent? That's a big question in the field of quantum physics. So unless you have a proper definition of the particle, you have to understand the essence of the coherent state, is because why all quantum optics books are dealing with coherent states to start with, is because unless you know what is a localized object which is analogous to a particle, you cannot have a proper applications in technology. So there are some standard definition of coherent state. I'll give you three of them, which is quite well established. So first one is annihilation operator coherent state. Annihilation operator already I described, and if you can find, if someone find an eigenstate of annihilation operator, say this K minus is in general notation, but for harmonic oscillator this is nothing but A. So A alpha is alpha alpha. So if you can find the eigenstate of annihilation operator, that will be a coherent state, and that is called annihilation operator coherent state, AOCS, annihilation operator coherent state. The second one is displacement operator coherent state. Displacement operator coherent state. Now it is seen that if you have a ground state of some physical system, say some molecular system, maybe harmonic oscillator also, then you define an operator which is this called the displacement operator. Okay, unitary operator, where K plus is for harmonic oscillator is A dagger, K minus is A, and alpha star is the one is conjugate, is a parameter. Alpha is a coherent state parameter. So if you operate this operator on the ground state, you are going to get the coherent state. So this is called displacement operator coherent state. Okay, and so for physical system, people are, scientists have been trying hard to construct coherent states since many years. So many physical systems people have already found, and things are also happening nowadays. People are trying to construct coherent states for different physical system, and for that you need to know what is the ladder operators, what is K minus, what is K plus. But harmonic oscillator, fortunately, we know many things. So this paper in 2005, we have actually given for some system which is a post-Taylor potential, which is also kind of infinite square well, which can also mimic chronic many model and so on. So yeah, so you can construct DOCS, AOCS if you know the ladder operators. Now this is a third definition, is minimum uncertainty coherence. It's a very interesting concept that everybody knows about uncertainty product, that the uncertainty in X and uncertainty in P is greater than equals to h cut by 2, right? So the upper limit, there is no upper limit, is greater than equals to, in quantum world, it is greater than equals to. But what is the lower limit? Lower limit is h cat by 2. So here it is equal sign, is not greater than equals to. If you find a state where you have the uncertainty product delta x and delta p, which is h cat by 2, then you call it as minimum uncertainty coherent state. That's a very special kind of state, minimum uncertainty coherent state, for which the uncertainties of position and momentum goes to a minimum value. Okay. Now, what is the physical essence of it? The physical essence is it is most classical. If you look at this sentence I have written, the state is most classical in quantum framework. So you create a wave packet, and that wave packet is nothing but minimum uncertainty coherent state. Then it will be most classical. So it will be a most appropriate candidate to describe a particle. Okay. So here is, this phase space xp I have written here, and so here this is the cross section. Is the cross section of the coherent state from above, and now the red lines are the distance of the coherent state from the origin. Okay, and this is also there. If you look at the coherent state, it's taken from internet, so you will find these plots very easily. So I'm using these plots where people, someone can take it from there, because these are all fundamentals. But probably it might not have written easily, but these are the plots which is given there. So the alpha, which is the modulus of that, is the modulus, the magnitude of the coherent state parameter. And this gives you the idea that how much it is shifted from the origin. You see, it is shifted from the origin, and these blue circles, it is shifted by this amount. What is the amount? Alpha cos theta. In x, it is shifted by alpha cos theta. In p, it is shifted by alpha sin theta. So that's the idea. So if you know alpha, which is a complex quantity given by mod alpha and theta, so you can know how much it is shifted in x space and how much it is shifted in p space. And you can exactly know where the coherent state is situated. I will come back more about it later when I visualize the coherent state over there. So in phase space, if you see in 3-dimensional plot, it will look like this. There will be elevations, which is nothing but the Wigner function, and then it is plotted in x and p quadrature. Okay. Now, what is the expression in the coordinate space? So can you find the expression in the coordinate space? For that, you have to write down this state in Dirac notation. So for harmonic oscillator, you know everything about it. You know everything about it for harmonic oscillator coherent state. So you can actually find out the expressions here. So I'll tell you the expression what is there. What is alpha? There is a summation of n. Forget about the coefficients in front. Summation of n, some factor, and then n. So it is a general definition of wave packet, if you remember, is a summation of n, cn, psi n. So psi n is replaced by n, cn is this coefficient, okay, and there is a summation of n. So it's a superposition of, linear superposition of eigenstates. Now, what kind of superposition? That's the question. Is a very particular expression over here. And this expression, depending on the parameter alpha, will give you the nature of the coherent state. So all that depends on Cn, and what Cn you want to take. If you take it appropriately, then it is nothing but a coherent state. And this is what I said is the coordinate expression of the coherent state of harmonic oscillator. Now look at it. It's very interesting to observe here that we knew, and I requested that you should remember the expression of the ground state of harmonic oscillator. This was the ground state at the bottom, which is a Gaussian, and this factor there, right? So it's a Gaussian, and Gaussian is centered at origin, x equals to 0. So if you put x equals to 0, that gives you 1. So it is centered at origin. Now here it is shifted by alpha. So y is a scaled x. So it is a m omega by 2 h cut, square root of that, x is y. So that factor is already inside it, but then it is shifted by alpha. This Gaussian, this is also a Gaussian, but this Gaussian is situated at y equals to alpha. So that means that it is no more at the center, but it is also a Gaussian, but it is shifted by amount alpha. If alpha is real, it will be situated on the x-axis. If alpha is imaginary, then it will be situated in the y-axis. In other cases, it will be situated in between, right? So now, because now we know about the coherent state and how to construct the coordinate expression of the coherent state. Now it is important that we know some of the properties why this coherent state should be known for a system, and we'll be doing everything for harmonic oscillator because that's the known system. Unknown system, these are all non-trivial problems, and each of the things can give you a new discovery. But for harmonic oscillator, things are very well known, and I'm going to point out this thing. So there is something called photon number. These are the things which people are connecting to different aspects in technology and in experiments. When the laser is built up, when you see a laser, that is nothing but a coherent state. So laser is composed of photons, is a coherent structure, and this parameter alpha, which controls the intensity of the laser. So it's a very interesting concept of the coherent state, which controls all the optics experiments as well as the experiments which is in quantum system. Now here, by photon number, what I actually want to point it out, as you know that all operators are mathematical entity. The operators do not have any physical connection unless until you apply the operator on a state. So this is the operator A dagger A, which is the number operator, and which is a mathematical thing. But if you apply on the coherent state of a system, then you actually come to know this scalar product, come to know that what is the average number of photon, because you're dealing with harmonic oscillator. Harmonic oscillator deals with laser, so it gives you an average number of photons in the state. Is the average number of photons. Or in other words, it can be said as photon number. Now this photon number, how it varies with n, is the quantum number n. X-axis is the quantum number n, and y-axis is the photon number Pn, and T is actually mod alpha square. So depending on alpha, these three plots are for different alpha. You can see the expectation value of n is 1, 5, and 10. So you can actually tune that what are the levels should be superposed. So I have a superposition, quantum superposition. So do I want to have a superposition which is 0, 1, 2, 3, 4, 5? Then this should be the appropriate coherent state parameter to model that system. But if you want to superpose from 0 to say some 10 or 12, then this will be the coherent state parameter. But if you do not want to superpose beginning states, but the later ones, then there will be coherent state parameter which is larger. Okay, so like that one can change the parameter and make the frequency of the laser. So this is the way one can change also the frequency of the laser, okay, and the width of the laser, everything by tuning this. Unfortunately, coherent states are not orthogonal. We always deal with, so don't look at these calculations, it is there. I have not removed that, but look at the last expression. This expression, that two coherent states, there will be a prime here in the second alpha. So if you have the orthogonality relation, then they are not zero, they are not orthogonal. Okay, so two coherent states are not orthogonal. That means they are not independent. Now there is a problem now. The problem is that in reality, when you measure coherent states, the measurement and distinguishability depend on the orthogonality. So if you have two coherent states, if they're orthogonal, you can simultaneously measure them in laboratory. But if they're not, you cannot. Then comes the positive thing I'm going to tell you, that if you take alpha, alpha prime, the difference more than 2, they are effectively orthogonal. So you do not have any problem if you go beyond certain minimum values of alpha, and all possible experiments we are actually using the larger values of alpha, and in that case we do not face any problem. problem in reality. But this is a properties that they are non-orthogonal, and they are overcomplete. So you may not know a state even who are overcomplete. So overcomplete means when you start quantum mechanics, we always know that there has to be in the basis, any state you take that should be written in terms of the others. If you can do that, then that's a complete set. But here you have some state which is more than the required. So if you take out one state from the basis, one coherent state from the basis, you'll be able to write another coherent state, another state in terms of the rest of the state. So this number of states which is required, that is more than the required. That is why they are called overcomplete. So this is the very salient important properties of coherent states. And this is very important, time evolution of coherent state, how the coherent state moves with time. And I just want to tell you this final expression, this one, that the alpha and alpha I omega t, this phase will tell you that how it is moving in phase space, because the real part gives you the position in x, the imaginary part gives you the position in p, and it is changing in time, real and imaginary cos theta, cos omega t plus minus I sin omega t. So cos and sin, these things are changing with time, 0 to 1. It is flipping from 0 to 1. That means that the coherent state will rotate in phase space, right? It will rotate in phase space, but what will be the radius? The radius will be mod alpha, which is fixed. I'm not changing alpha. I'm just changing the time. So in that case, it will be just rotating in phase space. So let me show it here. You see the coherent state is rotating in phase space for a given modulus value of the alpha. Okay. So radius is fixed. So it is rotating around the origin, about the origin of the phase space. Okay. And this picture again is showing that why it is away from the center. If it is at the center, it is not coherent state, it is a ground state of harmonic oscillator. As soon as you shift it, how do you shift it? You shift it by experiment. As soon as you shift it, you cannot say this is a ground state. It is a superposition of large number of states and a wave packet and appropriate description of particle. Okay. Now let me show you. I'm actually trying to go, kind of a smoothly to the applications. Now, let me see that what are the use of such states, coherent state. Number one, so I've given, so you should notice this number now. So I'll tell you the several usefulness of this state. First of all, let me see the Gaussian wave packet. When you look at a Gaussian wave packet, you see it decays. So when it starts from the beginning, it keeps on decaying. So, and then finally it goes down completely. So that's the very fundamental theory of quantum physics. A wave packet, Gaussian wave packet, decays as it propagates, right? But it is unlike coherent state. Coherent state does not do that. So which one is appropriate? Is the obvious answer to us that coherent state should be the appropriate one, which should oscillate inside the harmonic well. So if you have some harmonic well and a quantum particle, which is described by a coherent state, that will oscillate inside the well. As you can see here, this is the projection of this in some of the space. Say this is x, so it is in position. So it is oscillating inside the harmonic trap. Okay, and that's nothing but if you have a classical trajectory of a particle inside a harmonic oscillator, then also you see kind of oscillatory behavior over there. So coherent state is an appropriate description of it, which is almost a non-decaying wave packet compared to other kind of wave packets. Is the number one. Now what is number two? Squeezing of the coherent state. Squeezing. So you squeeze it in some particular quadrature. Now the top one, this is still a coherent state. I have not squeezed it. So this is a Gaussian from all directions. In Gaussian in position, Gaussian in momentum, Gaussian in some angle which is x and p and so on. But if you look at it, another state which is a squeeze state. Now you see it is no more a circular cross section from above, there is a squeezing happening in particular direction. So that direction is changing because squeezing parameter is time dependent here. So, but it is a squeeze state. One example, there are different kinds of squeeze states. So one example of the squeeze state of harmonic oscillator. So this is another applications, because squeezing is very important in quantum information science. If you introduce squeezing, then the state becomes more quantum. Okay, that you can verify in different ways. There are experiments for squeeze states. So this is the simplest demonstration for squeeze state. So this is usefulness 2. Now this is the third one, evolution under nonlinear energy spectrum. Now wave packet is decaying. So this is a coherent state now. And you see what happens. I'll just wait for a few seconds, and you see there will be small replicas of coherent states. Now you see if they are going to build up now, and you can see now there are say 5, 5, 6 and different numbers. It is going to change with time. And this is a very useful phenomena called fractional revival. Now it is 4. Now it is going to be 3, 2, 1, and again it will change, keep on changing. Now it is 3, okay, but they are replicas of the initial coherent state. And this is called the evolution. So it's a solution of the Schrodinger equation again, but the energy is a nonlinear function of time, nonlinear function of the quantum number. Say for optical fiber, if you look at optical fiber, is a nonlinear dependence of the quantum number on energy. If you look at hydrogen atom, it happens there. So it's a Rydberg wave packet kind of concept, and fractional revival for the wave packet. And recently we have kind of shown this phenomena for ultra cold atoms, and this was the first time we have come up with this phenomena in this system, which is routinely done in experiments, but nobody has pointed out in theory. Okay, so now number 4 is very interesting, that Schrodinger Cat State. Okay, now I have written briefly about what has happened. It's a very interesting story, and you must have seen this word Schrodinger cat in many popular places, in T-shirt and in different places in the website, and different messages coming in WhatsApp and so on. But what is it? Schrodinger himself found it hard to accept the probabilistic approach. When the quantum mechanics was in a very nascent stage, then Schrodinger said, what is this probabilistic approach? I don't believe it. Can the particle be in a probabilistic state? So that was very hard to, found it very hard to accept it. Then Born interpretation was a probabilistic interpretation. So according to Born interpretation of quantum mechanics, exactly 1 hour after the macabre experiment began. So this experiment I am going to tell you what is that. The box would contain a cat which is neither alive or dead, but rather a mixture of these two states. So what has happened, that there is a imaginary box, and you keep a cat over there, and you keep a factor that cat can be alive, cat can be dead after some time. So there is some factor inside the box. The box is completely closed, and then you do not know whether the cat is alive or dead. Now you ask, can this be in a superposition state, that it is also alive, also dead? And that was the confusion, raised by Schrodinger. I'll show you the picture first. You see, this is the typical Schrodinger cat experiment. Schrodinger has done this thought experiment and said that so he was trying to kind of nullify the concept of Born probabilistic concept. So what was there? You can see there is a lever, and the hammer is connected through a thread. This is a hammer, and there is a beaker of glass, and some poison is kept inside the beaker. Okay, and what is there in this box is radioactive element. And radioactive disintegration is spontaneous. You do not have any control over that. Now the box is closed. So, and then you keep a cat inside it and then close the box. Now what has happened? If there is some disintegration, now you go one by one. Step 1, if there is some disintegration that nobody knows, is anytime it can happen, then this will come down, this lever will come down, there's a faint position of it, it will come down, the hammer will fall on the beaker breaks, the poisons come out, the cat becomes dead. Okay, and I tell this again, there is some radioactive disintegration, lever comes down, hammer falls, beaker breaks, poisons come out, and the cat becomes dead. Okay, so directly, if there is some disintegration, the cat dies. If there's no disintegration, the cat becomes alive. So from outside, you do not know whether this cat will remain alive or dead after some time. So you just, then you think, Schrodinger said, so if this is the situation, can I say that the cat is in a superposition state, the alive plus dead? So that's quite absurd according to him. So what was happened after that? That was a very strong debate between them. And then Bond said, so here the mixture of states is not possible. That was said by Schrodinger. In the language of quantum mechanics, the cat wave function is a superposition of dead and alive wave function. Schrodinger thought this made the probabilistic interpretation of his theory a nonsense. Bond restored that as soon as, then Bond said, as soon as the lid on the box is lifted, if you just open the box, so we can observe the cat, then you see the cat, the act of observation. This is called the act of observation. When the box is closed, you do not know the state of the cat. You can consider there's a probability that the cat may remain alive. There's a probability that the cat remain dead. Okay. Now you open the box. As soon as you open it, this is a act of observation. Look at this word, act of observation, which collapses the state. Collapses to who? Either alive or dead. So it is no more a superposition, no more probabilistic concept. Either the cat will be alive or it will be dead. So that's how Bond defended his probabilistic idea. So that was a very, very famous experiment. Although he tried to kind of nullify the concept of probabilities, but he got Nobel Prize. Both of them got the Nobel Prize later on. And this was a very, very famous experiment. Now, let me tell you what is the act of observation. So Bond has said act of observation means when you open the box, then you find the cat alive or dead, right? So how is it? So let me give you a very simple example of how measurement in quantum mechanics happen, how the state is being collapsed. So, measurement in quantum mechanics is a very vast area, is quite, kind of a lot of things are there, but this is a kind of a very nascent explanation I can say. You have a basket of cherries, okay? A basket of cherries, many of them, all of them identical, assume all of them are identical, and we can see them. The cherries are very good, so it's looking very nice. And then you take one of them and test it. So while testing, you are also seeing the basket of cherries. So you are saying the cherries are looking very good and also it is very tasty. Okay. So cherries are both red. So when you are looking at it, the color looks red. Cherries are both red and good in taste. Okay. So you are seeing it, you are testing it. It is possible in macroscopic classical world. Now coming to the quantum world, you cannot copy. The state cannot be copied and kept in a basket. So you have a single cherry now. Okay. Either you took it without eating. If you eat it, then you don't see it. So it is red, or we eat it, it is good. If you see them, it is red. You eat it, then it is good. At the same time, at an instant, you cannot see the red cherry and also you can eat it. So you can have it in a different time. And for that, you have to have a different thing. But in a given instant, you cannot do this. So you cannot try both at the same time. The cherry could not be good and red at the same time. That's the basic idea of collapsing the state. So when you observe one, the state collapses to that. So you are observing it, you are seeing the cherry, then the result is, yes, it is red. Then you do not know the taste. Okay, or else you just eat it. You say, okay, cherry is very good or good in taste. Then you do not know the color. So that's the thing. So it's a probabilistic idea of the quantum measurements. Okay, so let me now go to the quantum system. What is it in the quantum system? This is a live cat. Okay, and this is a dead cat. So imagine that I have both the probabilities. Inside a box, you have a probability of live cat, you have a probability of dead cat, and the question is, can they be in superposition state, quantum superposition state? The answer is yes. This is a quantum interference. So both the state may not come physically one above another, but they can have a distant non-local superposition, which is the essence of quantum mechanics. In quantum physics, you can have a superposition state which has no classical counterpart. Okay, it's purely quantum properties. And you know, all technological aspects, quantum metrology, quantum communications, cryptography, and most of the fields are relying on quantum interferences. Now, if you have inclined some, a live cat and dead cat, definitely there will be superposition, but superposition structure will depend on that, right? So it will be along the line joining them, and you can understand that there are maxima, minima in the middle. Now take one of them. So I just take one live cat and dead cat, and this is a picture of Schrodinger Cat State. So this is famously called Schrodinger Cat State, and this is the starting point of quantum technology. Okay, so when you try to implement this state in laboratory, and there are Nobel Prizes by Harrows and Wineland, I'm going to tell you just now that implementation of Schrodinger cat, efficient implementation of Schrodinger cat state in laboratory. So a starting point of quantum technology by controlling decoherence and other factors. So if you zoom it up, and then you see that reds are all maxima and blues are all minima, and then you can have a clear kind of a sinusoidal functions over there is a quantum superposition structure. We have analyzed in detail about this structure in ultracold atoms for strong and weak measurements. So there are some recent development in weak measurements, strong measurements, and we have come up with the theory for that. Okay, and if you look at it in the quadrature, so this is a position, this is the momentum. I can say if I plot position here, and this is normally we in the horizontal axis we plot position. So then this is the position. You see here it is, and this is little broader because this I have cut it from my other picture. It will be little narrower, but you can see at least the scientific point of view. This is the position of the coherent state, this one, but you don't see anything in the middle because the average is 0. There is an oscillatory effect over there. But if you look at it in the momentum space, you see clear interference structure over there. So this is called quantum interference structure. In classical physics, you only see two states like this, but if you have a quantum interference, you see clear oscillations over there. Okay. Now the another usefulness, this is the number 5, which is Schrodinger Cat State, like this. Now a compass state. Compass means that if you go to C and then north, south, the directions, it should show the direction north, south, east, west. So if you have 4 states like this, there is one north, and then south, then east and west, and there are interferences. You see cat state, cat state, cat state, cat state, and then in the middle you have superpositions of the superposition. So it's a diagonal superposition, there is another superposition, and that's how it makes it a checkerboard structure at the middle. And these states are very, very useful for quantum sensing. Okay, and a generalization is also possible, and in experiment people have been trying to have more general superposition of coherent states to have more kind of modified technological applications. Okay, and this is quantum logic gate. And just like classical bit, you have 0 and 1, and you can also have a quantum bit. The quantum bit is written as qubit. Okay, and this is given by 0 ket and 1 ket. Instead of 0, 1, you have 0 ket and 1 ket. But the interesting thing is you can have enormous number of superpositions. And each point on this sphere, this is a sphere, and each point on the sphere, for example, this is this point, this circle, is 1 qubit. Now there are how many qubits on this sphere? The answer is infinite. And that's a very useful things in quantum physics, that because of quantum superpositions of 0 and 1, you were able to have quantum logic, the beginning of the quantum logic qubit, which is infinite in number in this space. So Hilbert space, which is much bigger than a classical Hilbert space. Okay, so that's the starting point of quantum logic gate. I have not included single qubit, 2 qubits gates, and those are there. You can build up quantum circuits, and one can actually give some circuit and have some computation in IBM virtual computation lab. So if that's free, some of them are free. One can go to the IBM website and give some circuit, design some circuit, and give them to do the experiment in their quantum computer. And then it will immediately perform the simulation in that computer and give you the output. Okay, and that's possible. So 8 qubit, 16 qubit quantum computers are possible to simulate. So you can simulate quantum circuits in IBM computation. So there are some pictures, Sudoku puzzle, and then artificial intelligence lab of NASA and Google. So there are different companies who are ahead of D-Wave is something who are manufacturing things. Okay. Now some very briefly before I end, some applications, just some instance, because I have not gone very deep into that, but then it is I found that I should point out some of the applications which we are doing, some of them. Okay, intense photon state, condensation of photons. The condition is that can I condense photons? Can I combine the photons in a particular state and creating experimentally some intense Fock state? Okay, so these are repeat slide. If you look at the distribution, which is Poisson, but if I go to a cat state here, then you see there's a n and minus 1 to the power n over here, and if n is even, this is still non-zero, but if n is odd, then this is 0. So that means if you have a combination of even combination, because alpha plus minus alpha, so the even states will only survive, not the odd states. You can see here these dots. So the odd energy levels, say for example, this is 12, it is there, 14, it is there, this is 16, this is 18, and this is 20, 22, and so on. There is no contribution from the odd states. These are the even cat states. Now, if I increase the pair of cat states, I'll be able to prove that I have the probability in only one level. So this is particular for 16. I have the probability of photon only in one level. But remember, I have started with large number of photons in different levels. All the photon has come to a particular level, which is, you can see the probability is 1 for this dot, which is at 16. And all other contributions are 0. So one can create such environment in experiment. And we have proven this in mathematical formulation and as well as numerical things. Okay, so this is the point of condensation of photons. Okay, so there are something we characterize the experimental values, the how many coherent state is required and what parameter, so that you get a particular condensation of photon, and we predict that this will lead to a photon condensation once we can see some particular phase transitions over there. And you can clearly see that in the beginning I have shown you the Wigner function, which is looking like this, but this is a Wigner function of the eigenstates. So this is for 16. So you have 16 zeros, okay, but this is not eigenstate. The point is, this is not eigenstate. This is a superposition of 16 coherent states. That's the beautiful thing of the result, that you can actually go from, if you change the parameter, you see they are not. So this is not, but in the middle one gives you the exactly at the Fock state. So we say that this is a dynamical condensation of photons. You can also go from quantum to classical. This is always a matter of debate, that how you transform from quantum to classical through some physical process. So this can be a beautiful guideline to do that. Then over complete to complete basis is also another aspect. Okay. Now diffraction limit. So what is the diffraction limit? This is the system here. And probably I'm overshooting time, and I'll just finish it within 5 minutes, this talk. And say we have these black dots are all coherent states. Now the thing is, can I consider these dots as some optical source of lasers? So if you have a source of laser, and then they should have a superposition in the middle, and we'll have a diffraction effect, right? So can this diffraction effect be compared with the quantum superposition? It's a completely different thing. One is optical superposition, and there is quantum superposition. So is there any analogy of these two? That was very beautifully we have connected. And we had to fight a lot with the referee, because referee was not convinced that there can be an analogy. And then we mentioned that there are some theorem called Van Cheetor-Jernich theorem, which is very famous theorem for diffraction of extended source. And there you can see that so okay, this is a chain of actual coherent states in phase space, but is a Q function. It's some other representation without interference. I don't see the interference here, but we have shown that this is the diffraction limit, where actually it goes to a diffraction limit. We can find a beautiful analogy for this state. Okay, so this superposition, which is the Bessel function, there are complicated expressions. I've just taken the variations in the middle. So it's a kind of Bessel function variations in the interference region. And this interference region, if you look at and forget about quantum mechanics, take a source of light in a chain. So the ring source of light, where things are situated like this, and then at the center you find a similar diffraction pattern. Okay. And this is the last one from my side, is the entangled superposition of states using cavity QED. I have not given the details of this. Some of the things I blocked because it's going on the scheme. And now is the Nobel Prize by Harrows and Wineland. They have this setup of cavity QED. Cavity is the mirror which is kept face to face, and then you can trap fields, quantum mechanical fields inside, and then send atom like this. Okay, so you have a field here inside the cavity. There are interferometers here, R1 and R2, which can make it as a superposition state, and then you send atom. So what happens when atom goes through this cavity, it interacts. Say for example that there is some registration desk here, people are sitting and they know each other, so they have a coherent superposition, which is a field, coherent state. Now some unknown person is coming in, okay, and taking some information. So who is the unknown person? Is the atom. Now atom is coming, talking to the people who are in the registration desk, and then going out. Now what is happening? These registration desk people have some information of this atom, and this atom also has some information about the registration desk. Even if it has gone out, both of them are having a mutual information exchange of information, and as a result they become entangled. Okay, they built up some relation between them and they become entangled. So in quantum mechanically, when the atom passes through a cavity, they become entangled state. And Professor Harrows and Wineland has beautifully kind of shown this for cavity QED, which I am just showing now, and ion trap, and got the Nobel Prize in 2012. So this is precisely the state system, which is their diagram from their lab. And we are actually doing something. So this is called decoherence. So they have controlled the decoherence to observe such structure. This is a kind of a compass state, which we have shown for a vibrating molecule that decoherence is affecting. So this is for harmonic oscillator, but for realistic system, it is very non-trivial as a complicated, numerical programming is involved because it is a asymmetric system when you go for molecular system. And but you can control once you know the effect. You can definitely control, and you see the structures are disappearing fast. That's a very beautiful thing. That these oscillations are diminishing with time due to decoherence. Now this is the lab by Harrows. Here the Harrows is here. So I met him just before in a conference just before he received Nobel Prize. This is a one-man lab. One man is in his lab. Now this is a schematic which we used. I have blocked some of the portion intentionally. I pardon for this. And this is a two cavity and atom is sent. Now the beautiful thing is that the atom goes from one cavity meet one registration disk, and then it goes on meet another registration disk here. They are independent. Now there it passes the information of the first registration disk. Then atom goes out. Now the first one has the information of atom. Second one has the information of both the cavities and the atom. So all two cavities are entangled along with atom. So that becomes a very interesting state in quantum physics, and you can actually generate such states. Now this is my last slide, where I'll show you that this is a cat state, alpha and minus alpha, like it is shown here. And you have another independent. So it's a cavity 1. It's a cavity 1 state, and this is a cavity 2 state. Okay, I alpha minus I alpha. It looks like this in phase space. Now imagine that I am making them entangled. What will happen? If I don't make them entangled, they're independent. There is no relation between these two cat states. But if you make them entangled, what happens? There is a checkerboard structure in the middle. There will be, of course, there are more structures over here and there, but in the middle you'll see this structure, and those are very, very useful for quantum metrology. So at the center you see we'll get such kind of structures. That's the idea we have implemented, and similar experiments they have done, and we are also talking to them, for implementing our results. But these are very complicated calculations. There are 64 terms in 2 places with dispersive interaction in the cavity. So this is one of the states among these 8 states which is here, and I would say that this is probably the most appropriate state for quantum metrology. Okay, so for the students and others who are interested, these are the reference which can be looked at if further things are required. In addition to clearing the confusions from me, later on one can look at it. So I thank you for your attention. I can take questions now.
Am I clearly audible now?
Yes, Shinjini, please continue.
Okay. So there are several questions. First one was asked by Diponjit Bose. He asked that, but sir, how Wigner interpreted phase space in quantum mechanics, since no conjugate position or momenta exist in quantum mechanics?
Okay. So yeah, so interesting question. And, yeah, is echoing second. Okay. So am I audible properly?
Rest of the participant, please mute your microphone. Rest of the participant, please mute your microphone. Okay.
Okay. So yeah. So the thing is that in Wigner distribution function, if you plot it in the phase space, you see x and p variables and the function itself. But there I mentioned that you can, the measurement quantities are probability density. So if you have a integration of one quadrature, you can go to the other quadrature, which is the probability density only in x. If you integrate over p, or else if you integrate over x, then you go to a probability density in momentum. So not xp, both related together. So this is one way of measuring the thing in phase space. Second thing is the Wigner function is also kind of measured experimentally, like a homodyne technique, tomographies. Okay, so what is done in tomography is you take a projection in particular direction. Say I have some theta angle in phase space, and I cut the wave packet, and measure it in a spectrum, and you see some wave, and then you take another plane and accordingly you go on with that. Then you can actually build up the whole Wigner function. So that's how you measure. So and then again, you are not measuring both simultaneously, one at a time, but it is a quantum measurements is a broad aspect, which is a probabilistic thing. So there are different ways of looking at the measurements, but you have to look at probability density. If you are measuring some observables, then it is the expectation value.
Okay, so the second question is also from him, is that can I say that these dx and dy are spread in eigenvalues of x and p observables? This question was posed basically for a particular slide of you, I think. Yeah.
Can you repeat again?
Yeah. Okay. Yeah. Can I say that these dx and dy are spread in eigenvalues of x and p observables?
No, see the eigenvalues of x and p. We're not talking about eigenvalues of x and p. Now the thing is, when you see the wave function, it is a function of x, and in Fourier transform it is p. Now question, when it comes to the position and momentum, you have to measure position, you have to measure momentum. So that means that you have to find out the expectation value of x, and you have to find the expectation value of p, and that's how you measure in quantum mechanics. Once you know the wave function, and then you expectation of x psi scalar product. That's theoretical approach of showing that this is the expectation value. For pure state, this expectation value is nothing but the eigenvalue of the position, and for momentum for all operators. Okay, and that's how you measure, how you go ahead with the observables measurements. But here I want to point out one interesting thing, that in Wigner function slide, in the bottom I have shown some relation with the overlap function. There is a scalar product. So if you know the two wave function, you can have overlap integral, and you can also have the Wigner function corresponding to that, and then you can distinguish two states. So like that also is an approach towards quantum metrology. You can actually measure a very small distance than it is possible in using other methods. So it's a much smaller precision you can have. So that is also another way of measuring experimentally. Okay. Yes. Yes.
So next question is from Orindam Mal. He is asking that, is wave packet representing a free particle non-spreading?
Okay. So free particle wave packet, if you solve Schrodinger equation, free particle has a sinusoidal nature wave function. Eigen function is sinusoidal. So any wave packet can be kind of a sequence. If you look at the Fourier series and all, then there can be a superposition of all plane waves. So, but free particle is not there in the reality. Okay, so that's the main thing. So if you go for so free particle wave packet, there are two things. One is whether it is a free particle wave packet or it is a free propagation of a wave packet. Probably you are talking about the second one, that I have a wave packet, and then I am looking at a free propagation. I do not consider absorptions and so on and so forth, dissipations and all. And that kind of thing I have already shown you, that it is, rotating without any dissipation and dispersion. So yeah, that's possible. Those are all free propagation inside the potential. So you do not have any dispersion, dissipation, but yes, you have a presence of the potential for which you have actually evaluated the wave packet. So that's the thing.
Okay, the next question is from Tania Patro. She asked that how squeezing states are generated.
Okay, so Okay, good question. Very good question. You see that there are interferometers. Like if you have, I have answered my slide, but I will not waste time to share it again. If you have two states and some superposition, and then that state, if you see the photon number, those are already squeezed. So this is one way of squeezing the state. Second thing is there are varieties of states called Keaton states, photon added state, photon subtracted state in experiments. Those are all squeeze states. So different ways one can generate squeeze states. And so it's not very trivial that you generate something in experiment and also have a corresponding exact theory, okay, to model that. So that's not, most of the time that's not possible. But whatever is possible is this, that there are different states which are can be implemented, which are already squeezed. But how to model it? You model with some squeezing parameter and then match with the states which you obtain. So that's the thing.
Okay, so the next question is from Shumon Mondol. He asked that how can we control the eigenvalue of annihilation operator alpha?
Okay. So eigenvalue of annihilation operator is nothing but a coherent state parameter. That's a very relevant question, I must say, that now it depends on the physical system. As I said, that alpha, if you're talking about only harmonic oscillator system, which I have actually talked about mainly, then compare this to a laser. It is easier to compare this to laser because you know laser very well. You see laser everywhere, okay? And the profile of the laser, if you look at the profile of the laser, if you plot the intensity, and then it is a Gaussian. And if you look at the coherent state expression I have shown, that is also Gaussian. And if you know, if you see the photon number over there, average photon number, which is mod alpha square, okay? And this mod alpha square is related to the intensity of the photon, the maximum intensity of the photon, okay? And this is related. So you want a particular intensity of the laser and you choose the parameter accordingly, okay? And that is exactly possible, and people have been doing it routinely in experiment, that how it is modeled with a coherent state parameter. So that's the way you should link it, average photon number.
Thank you. And then another question is from Norosima. He asked that each energy eigenstate of harmonic oscillator is a linear in frequency omega, whereas their coherent state, superposition of number states, most classical has energy proportional to square of the frequency omega square. Why it happens?
Well, there are two parts of this question. One part is that whether this is linear in frequency. Yes, it is linear. Harmonic oscillator has the energy which is n plus half h cut omega. So now you can, if you increase n from 0, 1, 2, so each energy, if the gap between the two energy levels, these are h cut omega. Okay, and so it is linear. So it is the same for all the levels, all consecutive levels. Now the second thing is that for coherent state. Now how to create a coherent state over there? Say I have molecule, diatomic molecule, which can be modeled by harmonic oscillator in the bottom levels for a very steep potential diatomic molecule. Then what is happening that people are using laser pump probe experiment and then to overlap the quantum states. Okay, and whether this energy, whether this operator is a quadratic of the frequency or not, it strongly depends on the system you are dealing with. For diatomic molecule, there are series of frequencies, like omega, omega square, omega cube, and so on. For optical fiber, it is a quadratic of the frequency, quadratic of the Adair square. So Hamiltonian is the square of the number operator. So it depends on which system you are using. So that's how. But for pure harmonic oscillator, it is linear. But if you go for a non-linear system, then it can be any power of the number operator.
Okay, and then Ajanta Dash, he asked for one reference of review article about quantum information, and also a similar question, similar request was posted by Salman Parvage. He also asked for some reference paper. so that the details
Okay.
of this topic can be understood better.
Okay. So definitely, maybe I'll send you later, maybe by email or so. Then I think Dr. Dasgupta can circulate to all of you. Maybe I'll give you some. I'll try to give you some review article which is readable. Like many review articles are not by thinking of graduate and master students. So so I'll try to dig out. I choose one of them or two of them, and then I'll send it to her later. I'll remember that. I'll note down. Okay.
I don't think that there is any other question. No, many of them have appreciated your talk.
Okay.
So,
Thank you.
and Upalana, I mean, is there anything more you want to share with us?
Actually, I confessed in the beginning itself. Many of the things I could not, go to the details of the things. So I had to go through the surface of the things because time is limited and then audience is mixed audience. But anyway, if someone is having some doubt any point of time, I'll be happy to kind of discuss later on as well. So that's the thing. So
Okay.
yeah, so we for the second talk, I think we have to take some break for a few minutes. What do you think?
Yeah, yeah. Maybe we can, or okay. I mean, it's up to you. If you can continue, we can continue. Otherwise, we can take
Yeah,
for.
I'll just go and take water and come back. That's all.
Okay. Then just let's wait
Just
for him.
I'll take a break of 2 minutes, and then I'm hoping I'm seeing the number of participants. I hope that it will not be reduced. So it is for the
Yeah,
students.
we also hope so. We also hope so because it
Yeah.
was a nice talk, and we hope that everyone have enjoyed it. So,
Thank you so much.
okay,
I'll be back in two
See you
minutes.
in 2 minutes. Yeah, sure. So participants, please wait for 2 minutes. Then our next talk, the second part of this webinar will begin. And at the end of the second talk, we will circulate the feedback link in this Google Meet chat box, also in the WhatsApp, I mean YouTube live chat box. You have to fill the feedback form. There is an anonymous form to get a proper feedback. But once you are finishing that feedback form, then you will get another link for another Google form where you have to fill up just your name, email ID, and your affiliation. So that will be used to generate the e-certificate, and that e-certificate will be sent to you within coming few days.
Okay, I am back actually.
Sorry to interrupt you. Basically, just one question popped up. Is that yeah, regarding your first talk, is that just a minute. Okay, Ravi Teja, he asked that why coherent state is not dispersive.
Okay. Yeah, it's a good question. Yeah, I'll just let me just open the second slide. I'll just answer this thing in a minute. Where is that? Okay, so the thing is that to introduce dispersion, you have to include the effect of dispersion. So far we have only addressed that how coherent states can be formed with the superposition of eigenstates. Okay, and but in practice, if you look at the coherent state of other physical system, which is not the coherent state of harmonic oscillator, then they will definitely decay, but they will propagate longer distance without decay. But they will decay after some distance or time, which is unlike coherent state of harmonic oscillator. So coherent state of harmonic oscillator is the only one which will not decay with time and distance. The reason, mathematical reason I have given in my slide, if you remember the slide where I have shown the time evolution of the coherent state, and there you have seen the Cat function, the wave function is having alpha e to the power I omega t. So e to the power I omega t is a phase which does not change the magnitude and also does not change the width of the function. So that is why it does not change the shape and height, both. Harmonic oscillator I'm talking about, but that's not the case for other physical system. Yeah, I think that is okay, Shinjini.
I hope so, and there is no more questions, so we can proceed with the second term. So we'll again take questions after the end of the second term.
Sure. So because we are overshooting time, I'll count 1 hour from now. What is your plan? Like, you can tell me now so that accordingly I can modify my lecture. So how much time I should take for the second lecture? 1 hour is okay.
Yeah, I think so.
Okay, fine. So is my slide visible?
Yes, sir.
Yeah, it's coming.
Yes.
Okay. So fine. So this is the same slide which we have shown, and I'll be moving to lecture 2. Now here it will be more of application to physical system. So you'll see the application in a more intense way. Definitely, I'll introduce the system which I will be talking about. So that's the idea. But application in which direction? Mainly quantum simulation, quantum information. Is because that quantum simulation is the direction in which you can actually simulate a complicated system, say condensed matter system, to a system which is much tunable. So I am going to talk about this in little detail. So it is about the Bose-Einstein condensate mostly. So I have concentrated only on that, because with the knowledge of the first lecture, I think this is appropriate now to get into this area. Okay, so this will be more or less outline, because this is a single system. I can precisely say that I'll start with some fundamental idea for young participants, and then these applications. Okay. Now, this is better to start with the statement by Feynman. This is only a partial statement. So the before that, we have to understand that there are many systems which are very, very complicated. Complicated in the sense, so when we find something complicated which we cannot solve. Say I have a mathematical problem. If I cannot solve it, then I say it is a complicated problem. But if I can solve it for a better student than me, and for him it is not a complicated, right? So that's the thing. So there are systems which is not, which is difficult to probe in experiments as well as in theory, that what is actually going on. And one of them is condensed matter system. Okay, condensed matter system, though there are a lot of applications, but the main thing is the tunability. It is not much tunable. The atoms and the crystals, they are strongly bound, and you cannot actually tune because they are not visible to outside lasers. So that was a long-standing problem in physics. See, not only condensed matter system, any system which is difficult to probe in. And then Feynman, that's the power of intuition of greatest physicists and mathematicians, and that is how different fields have evolved. That he mentioned, maybe we can use another simpler and better controllable quantum system. So I would like to underline these two things, that simpler, better, controllable quantum system to simulate, understand, and control these phenomena. So something which we do not understand in some system, we can choose a better system and controllable system. Okay, these two words. And this is probably the starting point of the idea of quantum simulation. Okay, now this is just a kind of a abrupt analogy I'm drawing. I just added up in the morning that interference of atoms in a STM, scanning tunneling microscope image. I have taken it from a paper, science paper, which is available in internet. And this is array of say 64 atoms. One can count. So there are several atoms. All these peaks are atoms. Okay, and in the middle you see it is interference structure. Okay, now so how it is appearing? So what is the explanation? What is the physics behind it? You can draw this thing analogy that you have arrays of coherent states. Why I have included? Because you have already attended my first lecture. So array of coherent states, and then you can have the interference structure, which is kind of modeled of this thing. So this can be a analogy of two completely different systems. This array of coherent state is actually implemented in different ways experimentally recently within circuit QEDs and interferometers and all, but this is completely a condensed matter array of atom system. Okay, now how to go ahead with matter waves or ultra-cold atoms? Okay, because we are talking about Bose-Einstein condensate, which is ultra-cold atoms and also matter waves. Now here it is very confusing, matter waves, right? So the two things which is contradicting, matter and waves, both of them sitting together, right? So question arises whether there is a matter or wave. So this is not a new problem. It is a long-lasting problem, and a photon is a cartoon of photon, not atom. The photon also has a self-identity problem. So when it is thinking that whether I am in a frequency of X-ray or visible or so on, then immediately it remembers that, okay, I do not know whether I am a particle or wave. Forget about my range of frequencies. So this is a self-identity problem of photon. And then comes the contribution by de Broglie's very, very powerful intuition that if radiation, which is basically a wave, can exhibit particle nature under certain circumstances. We have to repeat this thing. And since nature likes symmetry, then entities which exhibit particle nature ordinarily should also exhibit wave nature. You see that because the light, the photon can have both particle and wave nature, that was seen in Planck's blackbody radiations, then photoelectric effect and so on, then particle also should have a similar kind of properties. And then he has given this formula, which is h by p. P is the momentum, which depends on mass and velocity both. Now it will be a standard homework for the students, and to find out de Broglie wavelength of an electron and de Broglie wavelength of a macroscopic object like a ball. So if one calculates the de Broglie wavelength of an electron is 10 to the minus 10 meter, whereas the dimension of electron can be taken as 10 to the minus 18 meter, although there are different things that, I'm talking about a free electron from, some encyclopedia, but there are different studies about it. You see the range of this, 10 to the minus 10, 10 to the minus 18. So it's much, much bigger than the electron. So you cannot neglect de Broglie wavelength of electron. The second thing is, if you look at the same thing for the ball, which is 10 to the minus 34 meter, and the dimension may be 1/10 of meter. So it is actually more than negligible for a macroscopic object. So naturally, what de Broglie has pointed out is almost looks to be a very feasible theory. The macroscopic object, de Broglie wavelength may not be appreciable. The second thing is, the question comes to the contribution by our own person, Professor Satyendranath Bose. What he has done is a remarkable step he has taken. This is the letter, his letter to Professor Einstein in 1924, and he has written that I could derive the Planck's distribution formula, radiation formula. And that he communicated to Einstein for publication and so on. And he also mentioned that he was translating his paper and so on from German to English and so on. But you see that this is a very, very remarkable steps. Einstein also tried to derive this formula, Planck blackbody radiation formula, using his Einstein's A and B coefficients. But that time he did not know about the distinguishability of the particle. The concept of distinguishability was not known in 1916 when he tried to derive. And then he kind of adjusted the coefficients along with the Planck's formula, and then he finally could match it. But that was not a foolproof derivation. But Satyendranath Bose has given a remarkable steps. I'll tell you what are the steps now. That the distinguishability of the particle, and then they can have integral spin, and there's no limit that particle can be in a single quantum state. So these are the things, bold steps taken by Bose and laid the foundation of quantum statistics. So this is the starting point of quantum statistics, you can say. And then Einstein realized that, this is a very remarkable step, and then he modified to a massive particle. Now, if you look at fundamental things from the textbook of statistical physics about the quantum statistics, only for two particles, 1 and 2, and you have two states. So particle 1 is in A, particle 2 is in B state. Then the wave function can be written in a product. Similarly, if you swap the particle, you will have the wave function in this form. Now in this thing, swapping the particle, because they are identical, cannot change the Hamiltonian, and which suggests that you should have two possible wave functions, psi s, which is symmetric, and another is antisymmetric. Now if you take two indistinguishable particles, the concept of indistinguishability, then the antisymmetric wave function will vanish. If 1 and 2 both are same, then it will vanish. However, the first one, symmetric wave function, still exists. So that means if you keep two particles in the same state, keep two particles on the same state, then they will have symmetric wave function, cannot have antisymmetric wave function, which is the violation of Pauli exclusion principle for bosons. So later, this symmetric wave function particles were called as bosons. So bosons do not obey Pauli exclusion principle. So that is a fundamental thing which will be required in our understanding. Now there comes, this expression which is very well known as Bose-Einstein distributions. I have used this abbreviation because it's known to everyone. And you can see that E minus mu by kT, there's the existence of the chemical potential, which was the idea by Einstein. And this says that if you go to a high temperature, then the particles are distributed over wide energy range. That means that there will be a lot of energy levels which are relevant. And then effectively this one is negligible, and then you can go to a classical Maxwell-Boltzmann distribution. Okay. But if you reduce the temperature considerably, then what will happen? Your chemical potential gradually rise, and it will be almost equivalent to the minimum energy available to the system. I repeat again, the chemical potential will be equivalent to the minimum energy available to the system. So that may be the ground state of the system. That may not be the ground state, that may be some other level, but that is the lowest state available in a given circumstances. So a number of particles in single particle ground state becomes arbitrarily large. Why so? Is because when mu and E minimum, they're equal, so this quantity will go to 1, right? So E and mu both are equal for that state. I'm talking about, not for other states. Then the denominator is 1 minus 1. So it is blowing up, right? It is infinity. So what is blowing up is distribution function. Distribution function is linearly proportional to the number of atoms, number of particles. So number of particles in that particular energy level will suddenly blow up when mu and E both are equal. So that's the point where, according to Pitarsky, he says that at low temperature, significant proportion of atoms in a gas condensate in a state of lowest energy of the system. And this is nothing but Bose-Einstein condensation. So you are actually taking all the atoms to a particular state, ground state, and this is a new state of matter. This is no more a gas, it is no more a liquid, no more a solid or plasma. It is a new state, which is a Bose-Einstein condensation. Now coming back to what is BEC actually means. So here this distribution function, you know that how it goes on. If you change the temperature, load the temperature, then there will be some critical temperature beyond which the number of atoms in the ground state will rise up and touch to 1, which is actually all the atoms. 1 means it is scaled to a total number of atoms. That means all the atoms are in the ground state, where absolute zero temperature, and which is still a virtual limit. You cannot reach to absolute zero temperature till today. We are near to absolute zero, but not yet to absolute zero temperature. So, but in distribution says that all the atoms should go there. Now, if you look at what is actually happening as per the distribution, that atoms are distributed over wide energy range, but then if you go below that and ultimately to lowest temperature, then it will go to all the atoms to the ground state. Now this slide, it is from the Catalyst presentation. Catalyst is the Nobel laureate for observing the BEC of sodium atoms in 1995. I'll come to that a little later. So what is happening, if you look at the first rectangle on the top, then the balls are, these atoms are behaving like a billiard balls. These are high temperature. So their de Broglie wavelength is negligible. They are far apart. Now, if you reduce the temperature, you see the de Broglie waves are appreciable. Like, that's why I started with fundamental idea of that. But if you lower the temperature, is inversely proportional to the momentum and inversely proportional with the square root of the temperature. So if you increase the temperature, reduce the temperature, your de Broglie wavelength will increase. Now there will be some critical temperature for which the atoms, de Broglie waves, they start talking each other. So they are actually overlapping each other. So they become so large, they are no more isolated, no more independent, they are overlapping each other, and thereby forming this strong red line, and this is nothing but BEC. But of course there will be some atoms which are called the thermal clouds, because you are not at absolute zero temperature where all the atom should boils down to a particular state. Now when we are talking about this accumulation of atoms, and this is a experiment of rubidium 87 by the Cornell and Neumann, and if you reduce the temperature, you see there is a sudden jump in the density. Okay, And remember, this is in momentum space. If you look at the axis properly, this is a Vx and Vz. So two momentum directions. It's a two-dimensional plot of momentum space. Now it is rising up. Why it is momentum space? Because when you reduce the temperature, kinetic energy becomes negligible, right? So it is natural to expect a localization in momentum space, right? So look at the movie of the same thing, that this is the base, this is the atoms, and then there are two thermometers. Left thermometer is the critical temperature, and right thermometer is the temperature of the sample. Now, if this temperature crosses critical one, there will be a sudden jump. Okay, you see the sudden jump, and that's nothing but the point of BC, which is shown in these two plots. So this is called Bose-Einstein condensation of rubidium-87 because its Cornell Wyman has done it. Now, theoretical prediction and experimental realization. You can see the year. There are 70 years gap because it's a very difficult experiment, and they had to reach the coldest temperature in the universe. So 50 nanokelvin temperature is the temperature. Nowhere it was reported. On the other hand, they had to reach it in the laboratory. Okay, so that was the hurdles they have taken, but then finally, they could overcome in 1995 and got the Nobel Prize in 2001. So these are the salient steps. I'll come to that later again. I'll show this slide again and then come to that. Let me move ahead. So as we're talking about experiments, it is important that I mention about the main steps of the experiment, because this field is the experiment is a little bit ahead of the theory. A lot of things are happening in experiment, but the system is so non-trivial, is non-linear system, that it is not always possible to have a theoretical model. So laser cooling, you can have a gaseous sample, have a laser cooling, and you can see that Chu, Tanouchi, and Philip have got the Nobel Prize in 1977 for laser cooling with Doppler phase. It's a very beautiful physics that the laser is applied to atoms, and because of the Doppler shift, atom sees a larger wavelength, okay, larger frequency it says. Then when it absorbs, and then when it emits with the larger frequency compared to the actual frequency of the laser, because it sees the higher frequency. So thereby it cools down the sample, it losing the energy from the system, and that is explanation of the laser cooling using Doppler shift. Then they use a MOT, magneto-optical trap, magneto-optical magnet and laser, both are used. There is a picture for that. Is a magneto-optical trap. There is a magnetic coils and lasers from all the sides. And this is the step which was kind of very difficult since years. Then evaporative cooling is a very easy that a cup of tea cools down, and if you just keep it for some time because of evaporation. But if you create this evaporation in a very controlled way by using radio frequency lasers and tilting the trap profile, then you see sudden decrease of temperature of the atoms, and that's take it to nanokelvin, which is required for the BC. And this is the Ketali's lab, atom laser, and when I visited 2 BC lab and 1 atom laser lab, which I visited that time. Okay, now let us come back to the applications. So quantum simulation is the one which is important with matter wave. Now I have already introduced this word matter wave. Whether it is a matter or wave, is a wave of matter, right? Now, how to create quantum simulation, how to create an environment using ultra-cold atom BC for other system. So this is the repeat slide, as I said. I'll come to that, and basically I want to show you the sequence that first of all, the condensate is purely of quantum origin. It is a quantum matter. Okay, there is no classical counterpart, and this is a highly tunable object. Now you should correlate this thing to a Feynman statement. The system should be very useful. System should be much tunable. Okay. And the second thing is it occurred in momentum space. That is also obvious because you are dealing with ultra low temperature. Now, because it is in momentum space, it is a natural that you apply some external potential to trap it in position, right? So there are technologies which suggest that you can engineer trap. So trap means to trap the atoms, right? So you have to trap the atoms in which is a quantum matter, and using the highly tunable properties. So here are some applications in different directions. I am not getting into those things, but BC is also observed in space recently in 2018 and 2020. It is the atom interferometry using ultra-cold atoms that is also done in the laboratory in a space station, okay, or the Earth orbiting. So you can see the science paper, and why they are investing so much money for doing an experiment in space station, because they find that this is one of the most appropriate system for quantum technology, right? And the basic thing which you require here is the external trap. That means when students study that in Schrodinger equation, solve Schrodinger equation for different potential, external potential, I'm talking about that potential. So there should be some external potential, which I call it as a trap, because I'm trapping the BC over there, and that should be the prime tuning parameter. Okay. And I'll not get into this, but just look at the last equation. Is almost like a Schrodinger equation, right? Minus h car square by 2m del square psi, and so on. But except the blue circle, this term with the blue circle, that's a nonlinear term in wave function, and this nonlinearity is arising due to the atom-atom interaction. As I said, the atoms are interacting, and that makes the system nonlinear and non-trivial as well. So this is a nonlinear term in the Schrodinger equation. Sometimes it is called nonlinear Schrodinger equation, and this is the external trap which I was talking about, which is red circle. So Schrodinger equation with a nonlinear term in the wave function we'll call Gross-Pitowski equation, which is the dynamical equation for BC. Now it can be made Seeger-shaped. If you have a cylindrical, like just like a clay, if I give a larger pressure in some particular direction, I can make the clay elongated, right? Just like the shape I have shown here. So you can imagine a similar thing, that external potential in such a way, cylindrical harmonic trap you can apply with a strong frequency trap, so that the system dynamics is effectively in some particular one direction, and this is called Seeger-shaped BC. And then you can also kind of tune the interaction in that system. Okay, now I'd request all of you to not to see the kind of equations wherever I'm saying, just it is worth seeing that expression itself. But if someone is having some curiosity to know more, definitely I can come back and explain a little bit more. But this is a non-trivial system as a theoretical approach, so I have to include some very limited number of equations over there. Now you see this equation is nothing but the last one for a general approach, because if you have a tunability in the system, if you want to have a trap engineering for technology, then what you have to do, you have to make your system equation general first of all. And it is the term which is energy term. It is existing in Schrodinger equation. This is also there. You have scaled with the h cat square m and so on. Then it is a external potential Vxt, and this is a loss gain term. I'm not talking about it. And this is a nonlinearity which I already mentioned. But only thing is the coefficients are made x and t time dependent. So I have made it more complicated. Why? Because I want more richer and interesting effect on that. So I want to control the system, and for controlling I cannot restrict to start with. I have to start with, I have to make it very general. Then I can control. Okay, so I'll skip this. and there are coefficients which have to be simultaneously satisfied. It's a very difficult task, and we worked on very long time, and then and everything has to be simultaneously satisfied, and then your nonlinear equation will be mapped into. You see, this is one example which we have given in 2014. It looks too much mathematical, but it is not. The reason is, I'll tell you the reason. See, this is the potential and this is the wave function. Now the potential, there are parameters which you can actually directly map with the experiment. Okay, if you look at a particular thing in experiment, then you take a particular profile of the potential, you match the parameters, and then you get a corresponding wave function. So that's the idea. The idea was, can we unify the method? Unify means one method gives you different external potential. Okay, one can also try this for Schrodinger system or Schrodinger equation with external trap in absence of the nonlinearity. So same thing should work on there, except a little bit of changes. But this is the way we have given a unified method of solving a nonlinear Schrodinger equation. So this is some recent study which we have given for double well. You see, double well is a very useful system for quantum interferometry, atom interferometry, and BEC in a chip. So you can build up an electronic chip, with a BEC atoms, and there are much more use of this potential in the system. Now the question is, when you do experiment, when you do numerical studies, you do not actually know which parameter will work out. So you have to do a lot of trial and error, and then you mix up with the intuition and then get into the final thing. But if you have a well-defined model for that, you know which parameter should be taken. So we have given several demonstrations using kind of control of the minimum of the double well, and how to tune the double well potential for ultra-cold atom for attractive interactions of the atoms. So which we reported recently. Now coming back to quantum simulation of disordered lattice. Now disorderness is common, everybody knows about it, like defects, disorders, right, in the lattices, different kind of lattices. So can we have a similar environment of disordered lattice? That is the question. Okay. So for that, you need to know a BEC in a bichromatic optical lattice. Now, the one thing is very important to understand here and notice here, that this red thing, optical lattice. Now, what is the optical lattice? Lattice we know, and the whole solid state physics is starting with the definition of lattice, and there are Miller indices and so on. But this lattice structure, can this be produced by optics? So can you create a lattice using lasers? That's the simple thing. The answer is yes. You can create the lattice by lasers, by overlaying lasers. And if you can create a defects in that, which is created by bichromatic, two lattices, there are periodicities of the lattice. But if you superpose two lattices with different periodicity, because it is optics, I can do that. And that's the point of tunability. In real lattice, you cannot do that. You cannot superpose lattices as you want. But yes, if it is lasers, you can do that. Okay. So this is a simple example of optical lattice. What is it? It is a standing wave generated from counter propagating lasers. So imagine that two lasers are equivalent laser. The generation of standing wave physics, everybody knows that they come and superpose. The wave is propagating, but the resultant pattern, intensity pattern, is not propagating. So that's why it is a standing wave. So the intensity pattern, which is standing, is in this oscillation form. Now, interestingly, this intensity pattern can trap neutral atoms. So that's the very interesting thing which has come up, not now, before 20 years. And then huge, it has kind of evolved like anything, emerged like anything to build up different technologies in this system. So optical lattice is the best system for quantum simulation and also quantum computation information. So BEC in bichromatic optical lattice. So this is optical lattice. And how do you create a bichromatic? You see, is a short wave lattice, is a long wave lattice, and then you superpose both of them. And you can more or less understand that, you know, there's a minima, there's a maxima. So there will be a dip in this maxima, and then you do like this. You see the shape is no more a oscillatory nature, but you have these positions, the smaller minima. These are the position of frustrations, the position of disorderedness. Sometimes I call frustrations because in different literatures, the disorderedness is also named as potential frustrations. Okay, so these are the positions where the disorderedness coming to the picture, which is built up of lasers. And there are many papers, and these have taken from the physical revelators in 2012. Okay, and there are continuously, you know, a number of remarkable works. Now, especially this one, which is Nature Physics in 2008. You see a sudden spike. So it's a cigar-shaped BEC. You see, it's a kind of a cigar, one-dimensional BEC, and that's very useful in experiment because you can have a stable wave over there. You can measure experimentally very easily, and they are also stable. So you see sudden spike in a particular position. Remember that when we started with BEC, the localization was in momentum, but here it is strongly localized in position. And the reason they cited is because of the disorderedness in the potential. Okay, and that's the new thing they obtained. And this is in condensed matter language, this is nothing but Anderson localization. So this Anderson localization was first time observed in ultracold atom in 2008. Okay, and there you know, they have used this lattice. So it was our concern that, you know, whether we can give a theory for that. So although it was difficult, but then we started with this. I'm not getting into this. Look at this potential. What is this? One optical lattice, just like, oh no, they have taken, everyone has taken in this form. So is a real lattice, V1, V2, they are related to the recoil energies, and L is a parameter, the periodicity of the lattice. So you can have a superposition of L and 2L, then you can create a bichromatic, is the two color of the lattice. Is a one color and two color, you overlap both of them. So this is the situation. We go ahead. This is the final result of the mathematical expression. Result means only mathematical expression. Next slide, I am going to show you how it is actually looking at. Now we mentioned, you know, we reported in laser physics letters in 2014, and we say that where from this tunability comes into the picture. One does experiment and tune it, but by changing the parameter, you may not know that how your condensate will change. Okay, and here we can exactly address that, you know, how the changing of L and beta, these two parameters. So we identify two physical parameters which will control the whole system. Okay, one is beta, another is L. Whole system is starting from the potential to the density, and we can actually have the desired density in the experiment if we map this theory to the experiment exactly. So now let me go to the plotting of this. Now you see, if the lattice, the background oscillations, this faint lines, these are all, you know, lattice, and the field plot are density of atoms. Density of atoms. Now, if it is a simple optical lattice, but if you see the y-axis, the value is negligible, very small. If you create a lattice with oscillation amplitude very small, then the atoms do not see the lattice. But how this maxima is coming in, it also will appear in free space without potential, because atoms are attracting each other. Inside BAC, atoms are attracting each other. So they pile up. They pile up at the center here. So no effect of potential is seen at this point of time. But if you increase the depth of the lattice, now you see the atoms started seeing the lattice, started seeing the external trap, and these maximas are in the minima. So if you have the idea of the bound states in quantum mechanics, wherever you have minima potential, negative potential, you are expecting a kind of a maximum intensity over there. And the same thing is slowly appearing. So there's a modulation, beautiful modulation over the density inside the potential. Now comes more interesting thing. There's no frustration, there's no disorder, but there's a big jump in the parameter 0.5 to 4. But if you smoothly take it, you will understand how it appears. They become more and more towards center, and suddenly when this disorder, the small depths in the potential, periodic small depths, this place, just touching zero, they started going to a negative potential. Then all the atoms come to the center. All the atoms jump to the disordered place. Is a very, very interesting and surprising fact, that when the disordered potential depth comes to the negative potential, and then all the atoms gradually starts going to the center. So I could not plot beyond this parameter. If you just increase a little bit beyond 4.7 or so, then you see there is no maxima around, only there is a spike like delta function in the middle. There's a strong localization, which is nothing but, Anderson localization, which is pointed out in the Nature paper. And we have verified with, energy plots and number fractions. And these are the things people measure in experiment. So number fraction and the energy per particle. So, and we have verified and showed that, yes, we are into it, and this is nothing but Anderson localization. And we have also added, a beautiful thing called dark soliton. Soliton, I have not described it because then it will be off focus probably, but is good to say a few words about it. I'm using bright soliton, dark soliton. What is soliton? Soliton is seen everywhere. You can see in water also. There are some waves which is propagating longer distance, very long distance without decay. And those are nothing but soliton. So soliton appears in nonlinear system. Water is a nonlinear system. Optical fiber is a nonlinear system. Atoms, collection of atoms, atomic system, that is also nonlinear system. And BEC is also nonlinear system. So all nonlinear systems, if you see a kind of a coherent state kind of excitation, that is nothing but soliton. And there is a physical way of generating it. Your nonlinearity and dispersion should balance each other. Then only there will be a stable wave in the system. Because it is stable, it is very useful in experiment. Okay, and remember, it is not a soliton in water. It is soliton in a quantum system. In a quantum system. So that's very important. So here it is dark soliton. That means the atoms are there is a deficiency of atoms somewhere, because atoms are pulling each other, they are repelling each other, and then there's a oscillation in the background, modulation, and we predict a bright solitary transit. You see, from dark to bright, we can smoothly transit by changing the disorderness of the potential, and that's a completely new proposal which we have reported, and this was quite kind of selected as the selected article of the year. Now, this is a very new concept which will be kind of interesting to the students, especially, and to others as well, that negative absolute temperature. So this idea may be new to many of us, and but this is not a new concept. In statistical physics, in the textbook, it was described that there can be a situation theoretically that you can have the temperature scale, which is negative. And what is the situation? So let me describe it here. In positive temperature scale, so far we have been talking about positive temperature scale, where if you increase the energy, the number of particles will go down. So imagine that the ground state will have more number of particles, more number of atoms compared to excited states. So that's the situation for positive energy values, positive energy scales, which starts from 0 Kelvin to higher Kelvin, infinity. Now, if you have the atoms in this fashion, so you increase energy, but number of atoms is also increasing. So you have the highest number of atoms, which is not at the 0 energy or the lowest energy, but a higher energy. This situation is completely new in reality. In reality, you never see such situation, because to achieve such thing, you have to have upper bound in energy in the system. The energy should be upper bound. There are, this situation is difficult and very difficult to create upper bound in energy. But in the experiment in 2013 in science, they have created upper bound in energy in optical lattice. And in they have trapped ultra cold atoms. Why this is possible? Because this system itself is so tunable. And so this is the first system for which negative absolute temperature is achieved. So if you have a such scenario in the distribution function, if you remember, no situation can permit it except you convert T to minus T. When you have T to minus T, then only you will have higher number of atoms in the higher energy state compared to the lower ones. So that is the situation they have created in laboratory. So very interesting experiment, and this is the one which LD Carr has explained this in Science 13 in the same issue. This is the figure which I have shown to you, and this is the kind of potential they have used. You see at the bottom one, this is the final potential they have used, and this is the density. Now this potential is optical lattice, as you can see, is an oscillatory thing, but along with that there is a expulsive effect of that. So it's the opposite to harmonic trap, right? And naturally, if you have a normal system, it will not stay there. But because it is optical lattice, they can trap atom over here. And that's the kind of key to do in experiments. Slowly they change the potential and take the atoms to the higher states. Now, this is the momentum space. In negative temperature, things are atoms are accumulated in higher momentum space, not to the center. This is the center in positive momentum space, but you have the accumulation in higher momentum space. And this is the potential they have taken. You see the optical lattice is important to see the potential now. Is optical lattice time dependent coefficient, because they're changing it. And this is Z square, means harmonic trap, harmonic potential, and then time dependent. Okay. Now what we did, what is our contribution over there? We have modified it. Why it is so? We have modified this way. We have changed the optical lattice to bichromatic, 2 optical lattices. All other things are there. You have this term, you have everything, but then in place of optical lattice, we take 2 frequencies. Okay. And why so? Because one case of this, you know that goes to optical lattice. So this is a much more general case that than the optical lattice, because a special case of bichromatic lattice goes to optical lattice. The second thing is, a bichromatic lattice offers a better platform for quantum simulation. You can have such effect if you have in presence of bichromatic lattice. You can expect such effect in condensed matter physics, whatever you are observing. Okay, so now directly moving to the form of the potential, which is and this is completely exactly mathematical. No approximation is involved. Starting from the fundamental dynamical equation, we could crack the problem. That this is the first theoretical development where there is a strong localization in the higher state and on the negative absolute temperature. And so you can see that not only we obtain this exact model for negative absolute temperature, but also we see a transport of atoms. Transport of atoms, atom distillations. These are very new things. People have been trying in interferometry a lot. So we have incorporated linear trap, which is routinely people have done in experiment to tilt the trap and have atom distillation of this kind. So if you see the bottom right corner plot, this one, then you'll see that how atom is distillated. So this is position and this is time, and it goes from one well to another. But remember, this is in the system with negative temperature. So the temperature goes from 0 to minus infinity, not to 0 to infinity. It goes to 0 to minus infinity. Okay. And then we verify with different things. We exactly calculate the temperature. And we also show that the fluctuations in the disorderness enhances the negative temperature. Since not only that we get it, we say that we are able to propose a more stable state in negative temperature. And second thing is, the temperature will be more negative. You can see minus 14, minus 338. So temperature is more negative as we increase the disorderness in the system. So similar effect can be probably observed in other system of similar kind. So this was recently reported in scientific reports. Well, so this is a very new development. We are doing a number of things, but just one slide I have devoted to mention this thing because this is also another direction people have been working on. So there's something called rogue wave. This word. And the rogue wave is very surprising. It appears in sea from somewhere. Nobody knows where from it appears and then suddenly disappears. But this wave has a very particular character. You have a strong peak and also has a minima along with that. So you have a peak, you have a minima along with that. And it's a very, very strong intensity is very, very, very localized and strong. And this wave is very surprised wave and observed in disordered system, nonlinear system. And we wanted to see that with quantum simulation. So we have seen in coupled BEC, single BEC, both the things. So I'm not getting into this thing. So you can see here, this is a rogue wave. Why? It is a maxima, and you see the plots are very small, but you can see there is this y-axis, mod psi square is the probability. There is a region in negative also. But did you see any density, which is mod psi square, which is negative? If you remember, Eigen functions, wave packets, and whatever you have seen so far, there is no negative region in the probability density. Probability density is negative, is always, all the places are positive, most of the cases. But here you can see is a positive and negative both comes together. And then we check it for Anderson localization for disorderness, and then we achieve that. So at center, this range is very small. So we have zoomed up, and then to show that there are negative region, you can see below 1 and above 1 is the Anderson localization for rogue wave, matter rogue wave. Okay. Okay. So this is the last one probably for the quantum simulation. So okay, after that I'll be telling you a little bit about quantum sensing, and then I will end. This is the engineered lattice. Now this is the parameter of the lattice. You see the lattice is changing in such a manner that you can probably have varieties of things. So this is the no, let me not go into the kind of density we get. Let me show you the potential. You see the potential is here, is a periodic, but not a optical lattice, not a disordered optical lattice, and so on. But on the other side, you have a double well superlattice. Double well superlattice is a very useful one in quantum interferometry, quantum simulations, everywhere. And not only it is a double well superlattice, we also create disorderedness in between double well and a separation of the double well. So it is a much versatile trap, and probably the most in the literature, because we actually show the continuous tunability of it. Why it is possible? Because here we superpose optical lattice of 4 frequencies. So we name it as 4-color optical lattice. It's a 4-color optical lattice reported for the first time. Okay, and yeah, so now quantum sensing a bit. These are very important directions in quantum informations, and this is the recent one which we have observed in with matter wave fractional rehearsal. And this is a system. You see a ring. It is actually a potential ring, and the red one is the BC. So I keep BC inside the ring. Now what happens? You see, it splits into different numbers. Okay, and this is called fractional rehearsals, which I also mentioned in my first talk. Okay, now there are experiments. There is some background noise somewhere. So there are several experiments for this persistent flow of this atoms, bases, right? And then we actually model this. This is our engineering of the trap. We tuned it in such a way that we create a very stable ring potential, and as they have done in the experiment. And we actually say that in what limit you are going to get a potential which is a stable ring, and you have a consistent flow of the cloud inside that. Cloud means BC. So you can see a BC, this peak. The white ring is the ring, and this is the BC. Okay, so this is exactly the system of ours. And then you observe for longer time. So what happens? So let me show you the movie that for 2 things. So you have a ring. Imagine that you have a ring of like this, and you have 2 BCs. Why 2 BCs? Because the movie is ready for 2 BC. Single BC, we don't keep it with us. We initially made it for 2 BCs. But the same thing will happen for single BC also. So let me do that. You see there are occurrence of, I just stop somewhere, and you see there are patterns. So there are, this is, what is this? This is the probability density of atoms below critical temperature. Now if you run it again and stop it somewhere, there was a 4 split up, just, you know, I crossed it, I could not pick it up. But then if you stop somewhere, you see, now it is 6. There are 6 clouds inside the ring. And then so on. You can just keep on going it, and then you'll see different number. There are 2, it was just 2, and then it will go on. And this comes back to the initial one. When it comes back to the initial one, it is a revival, which is, we found 2.37 second, very consistent to the existing experiments. And this is the precise thing which I already explained in my first talk, so I'm not getting into that. You get different splits at different particular time. We exactly mention which millisecond and what instant you get snapshots. All this speaks of density, and you are actually doing XY plane. This is a position plane, remember. So I started with that you have to have potential, you have to engineer potential to control clouds, and that's what is going on in technology. And these are the things which we exactly observe for the new phenomena. And then we verify with autocorrelation functions and quantum carpet. This is called quantum carpet, and this is autocorrelation function, where we exactly say which time, how many clouds will be appearing, and so on. And this is the stability, that whether it is stable enough or not, that is being pointed out. And then we analytically proven. So these are all numericals, and we give a parallel theoretical approach, exact theoretical approach, to find out the time scale. And then we verified it, that how ring radius and other things will vary. So new formula emerged from this study as well. So this was reported recently in Physical Review. Okay. Now this is from that system. You see, if you run this thing and see that the central region, if I switch off the trap, central trap, then the cloud is come to the center and they'll superpose and we'll have in this fashion. But it should be actually like this, right? So we'd expect that there are sources along the ring, and when those clouds are rushing towards the center, there will be a circular rings of this kind, maxima, minima, like we have shown circular arrays of coherent states. But it is not. It looks like this. The structure is very different, and we worked on that. It's a beautiful correlation with the phase, and I'll show you when we switch off the trap. Now this is not the same movie. We should notice that center should have this kind of superposition, which is in XY plane. So we have not switched off. Now we will switch off, and it comes to the center. So I should be able to catch it. I am not able to. Yeah. Now you see, at the center, when they cross each other, and you have this interference effect, which is a real spatial interference. You don't have to go to the phase space, and which is quite different from people know in the literature that the cloud should have. So, and then we have the particular explanation for that. And the last one, which is in a couple of minutes, I'll be doing it. The last application is quantum sensing, a direct approach. We have communicated, but I would like to mention to you some of them, not all the results. And this is a very beautiful one, tunneling and reflection. Simple thing, when all students know about it, that when wave comes, they can say optics. I have a slab of glass slab, and then the laser is falling on it. A part of it will be reflected and part of it will be transmitted. But in quantum mechanics language, the transmission is right. So tunneling and reflection both happens. So if you look at this one, then this is a tunneling and this is a reflection. Okay. If you create a barrier, then you find both of them together, even for quantum mechanical waves. Now there are experiments. Let me not get into it, but show you this movie. The middle one is the barrier. Wherever you see a spike, a red spike, that's the barrier. And the blue Gaussian like this is a cloud. The density of atoms in BC. Okay. Now let me run this movie and see. A barrier is coming, is striking, and is reflected as well as transmitted. So this is a transmitted, tunneling, and this is now I create two things. Then I remove the barrier. You see so beautiful dynamics inside the trap, and all these small spikes, those are all interference structure. Okay. Now look at it again. I'll be putting two spikes now. Yes. Now I remove the spikes. I do not have any Gaussian peak now. No laser. Now it is evolving freely. Okay. Now you can observe at some certain instant, and we have actually kind of mapped it to a beam splitter, atomic beam splitter, which is a very exciting thing in recent times, that it can be like an atomic beam splitter, a very sophisticated atomic beam splitter, which can lead to a sophisticated interferometry. Now this is the kind of structure we get. Say I observe the cloud in 11.2 milliseconds, which is with experimental data, with the experiment by Schrodinger et al. in Nature paper 2001. And so if you look at this cloud, the center part is zoomed here. You see the interference structure over there. Because it is interferometry of atoms, atom shows such kind of interesting structure. And why it is so special? Because this structure has zeros all around. Okay. And the structure which is having a zeros all around, was very much useful for metrology. And you see, and the GPS and everything is now controlled by quantum metrology. It is no more previous classical metrology which is being used. Even Indian Standard Time is actually regulated by using quantum metrology. So the precision of the time, which is governed by quantum metrology in National Physical Laboratory. And quantum security and many things in the government offices, ministry offices, they are actually in confidentiality and all, quantum cryptography communication is being used. So this is something we lead to a scaling law for quantum metrology. So how to do quantum metrology in theoretical thing for ultra cold atoms. So there is no scaling law which can give you a precision measurements. So we actually come up with this scaling law. This paper is a Nature 2001, where it is first time reported that for harmonic oscillator and chaotic gas. Okay, and now we report for ultra cold atom. Law is valid and is surprisingly valid, I would say, because it's a completely different kind of system. We take measurements for different time, and then we show that yes, it is indeed maintaining the relations. Okay, and at the end we also have an indirect measurement of temperature. So that's the new thing in ultra cold atom, that people have been measuring few nanokelvin, but we are able to have a precision of picokelvin temperature. These are indirect measurements of the temperature using this precision interferometer scheme. Okay, so the closure is that we have I have started with the fundamentals of Bose-Einstein condensate, and why one system I have emphasized, because then I can continuously move on to advanced applications without much explanation for each of them. And then we said that controlling this system is very much tunable, and controlling it is especially depending on external potential, although the scattering length also can be tuned, but here I only mentioned about external trap, which is a better method. Okay, and then I explained some of the applications where new phenomena, quantum simulation and quantum sensing is involved. So these are the things which is going on in recent times. People have been working intensely on quantum sensing for this system. So these are again some references which is relevant to my second talk, and one can note down and see later on as well. And this is my group. These are PhD students, and this is master's project student, and I am thankful to my collaborators for these works. So thank you very much for attention. Yeah, so I can take questions.
Yeah, thank you, Dr. Roy, for this nice talk. Several questions are there.
Okay.
First question was from Diponjit Bose. He asked that instead of many boson system, if we take only one boson, then can it form the condensate alone in its ground eigenstate?
Okay, so yeah, I said that the origin of Bose-Einstein condensate relies on the fact that they do not obey Pauli exclusion principle. So the idea is one atom can have energy levels, but here the overlapping of the energy levels can give you a wave packet. That's a different thing which I have talked in the first lecture. So pump probe method can be used, and different methods can be used to create wave packets. But here we have talked about the superposition of atoms. But how to superpose is a quantum superposition. So if you think that each atom is a wave, then only you can explain such state which is called Bose-Einstein condensate. So it is a superposition of neutral atoms. So there is no analogy for single atom.
Yeah, hope that makes clear to Diponjit. His next question is that in B statistics, does we also have to account for the energy time uncertainty principle when we want to analyze and measure to which particle is in which energy state?
Okay, so now it is a mix up of a lot of things. I would say that just like, I have talked about position and momentum. There are a lot of studies for energy and time, of course, and then the phase uncertainties. So those are possible equally, but it depends on which one you want. Say you want a precision in momentum, you want a precision in position, then you have to look for the delta x delta p, and that's actually is the mostly used uncertainty relations for practical applications. But yes, energy time, because the time is not the thing, like just like you observe in spectroscopy and absorptions, this thing absorptions spectrum. So those are the things used in a different applications, not the applications kind of applications I have mentioned. But anyhow, people have been working on all sorts of uncertainty things, and which is not a disadvantage. So the whole study is what I explained. The uncertainty principle is no more a disadvantage, but it creates advantage, because the smallest structures, which is much smaller than uncertainty Planck's constant, but it is not violating uncertainty principle. So it is not obstructing you to measure a much smaller dimension, which is much below Planck scale. So yeah, so that's
okay. The next question is from Sheta Pal Mojumdar. She asked that, is there any time independent GPE like time independent Schrodinger's equation?
okay. So you see how you make a Schrodinger equation time independent, because you have to have a stationary solution. So stationary solution is the one which is not moving with time. But similarly, in GP equation also you can have stationary solution, and definitely then you are not actually looking at the time evolution. So that's possible. Yeah. In experiment theory both.
Thanks. Next one is again from Diponjit. He asked that in nonlinear Schrodinger equation kind of mechanics, does the observable theory and vector spaces formalism come into account? If not, then how do we deal with those systems?
No, can you repeat?
Sure. Yeah. He asked that in nonlinear Schrodinger equation kind of mechanics, does the observable theory and vector spaces formalism come into account? If not, then how do we deal with those systems?
Okay. So first of all, what I can extract from the question is that this nonlinear Schrodinger equation is an equation. The origin is completely different, but your question is not the origin. But I'm just mentioning because the beginning part was the basis, because the psi what you see is the order parameter of the condensate. Okay, so because it is the system after, now I have to use a little bit of technical things, is after the second order phase transition, and psi is the order parameter. And fortunately, this psi mod psi square gives you the density of atom, but it is not a single atom, it's not the number of atoms, it is a cumulative effect of the density due to atoms. So the measurements, just like in a Schrodinger case, you can create a wave packet with psi 1 plus psi 2 plus psi 3 and so on, linear superposition, C1 psi 1 C2 psi 2. But here it is not. Here it is not the superposition of energy levels, it is the superposition of the atom itself, and after superposition they create a single state. It's a single state. So, and the measurement becomes direct measurements. So we have a system which is the wave function itself. The density, if you do, is not eigenstates, it is the cloud itself. And when you measure, say absorption imaging, you measure. So time of flight measurements, you measure. Then you clearly see the image of the cloud. Like I know I have shown in probably towards the end of my quantum simulation part, our theoretical, so exactly similar image you get in an experiment with absorption imaging. Okay, so you directly image the cloud. So that is much better than the wave packet concept. Yes. Okay, can I have the next?
Sorry. Yeah, sure. Yeah. Okay. Next is from Tania Patro. She asked that if we live in quantum world and if Planck constant equals to 1, its value is 1, then can we see our so-called classical objects like table, chairs at a fixed position?
Okay. So first of all, you cannot take Planck constant to 1. Either you have to have it or you don't have it. So you cannot change the Planck constant. That's a universal constant which appears unavoidably in fundamental units. Now the thing is that the system where you have the H card, then you can more or less see that this is going to a quantum system. But and I said in my first talk some of the classes. So quantum classical correspondence is a debate forever. It will never end. Okay, but you can at the most address it from different directions. Say if you see from the fundamental quantum mechanics knowledge, Bose correspondence principle, Ehrenfest theorem. These are the ways you correlate with classical and quantum in different aspects. And in advanced applications, like diffraction limit is one thing. And then coherent state can be laser as well. So like that, you can correlate the things. And uncertainty, if you go to a quantum domain, then it is the minimum uncertainty. But you are applying to a quantum system. You are not applying to a chair and table. Remember, you cannot. That's what I started with de Broglie where, and I mentioned that for macroscopic system, that's not relevant most of the times. Yes, macroscopic system can be quantum in a different circumstances. Say black holes and different effects, and normal modes of black holes, and those are the things. But there also you take into account the quantum effect. You are dealing with atoms. Okay, so that's the thing. When you are dealing with microscopic systems, you are not dealing with chair. When you are dealing with the atoms of the chair, then you are dealing with the atoms. So the domain is completely different. You have to decide beforehand. The system will not tell you whether, okay, you explain to me using classical physics or quantum physics. You have to decide one approach depending on your interest in applications. So that's the thing. It is very important. Before going for any application, you have to decide the system, whether it is an atom or the chair. The second thing is what application I want to have. Do I have the application that how atom is moving, how the scattering is happening? Then chair is immaterial to me. But when I am applying the Newton's law of the chair, then immediately I understand, okay, I do not need to think about quantum effect. It's the classical laws of motion. So that's the thing. Yeah.
Okay, thanks. Then the next question is from Diponjit. He asked that at negative temperatures, how can uncertainty principle will be obeyed, as we know motion ceases at T equal to 0 Kelvin?
Okay. No, negative absolute. Are you talking about absolute zero temperature or negative?
Yeah, basically his question is that at negative temperature, how uncertainty principle will be obeyed, since at T equal to 0 Kelvin, motion ceases. That's what he's asking.
Say I have this pen with 20 degrees centigrade. Now I am saying that is a plus 20 degrees centigrade. If I say it's a minus 20 degrees centigrade, what is going to be changed for this pen? It's nothing. So you are not crossing positive to 0 to negative. No, that's not possible. Okay, you create a situation, and there may be a situation in the physical system that is being observed in experiment, that you may have a situation where you have to define the temperature in the negative domain only. So that's the thing. And after that, all the laws of physics will obey as it is. So uncertainty principle, observables, measurements, everything will go as it is. Okay, so there is no problem in that. So we have been studying in negative absolute temperature with interferometry and a lot of other things I could not mention. So those are possible, not a problem.
Okay, thank you. Then I hope the last question is from Orindam Mal. He asked that if tunneling is a general if tunneling is a general happening, can we actually confine a wave function in 2-dimension or 3-dimension box like we do, or there is tunneling also?
Okay, so
Probably really he is asking about whether we can confine it within a 2 or 3 dimensional box, or everywhere there should be some kind of tunneling for any kind of quantum system.
okay. So if you look at the tunneling amplitude, fundamental quantum mechanics book, then this depends on exponential factors, and then if the alpha a, there is a coefficient, right, depends on the width of the well and width of the barrier and height. So it all about you model, how do you model the barrier, but this tunneling amplitude never ends. So it goes to infinity, okay, but it decays. Now the thing is, if you increase the barrier width, then it will decay. It will be reduced, considerably reduced. So accordingly, now convert this barrier in all the sides, not in a single site. Now convert this step well or maybe potential barrier problem to create a barrier in all the sides, and then you can imagine that there will be tunneling even if you keep the barrier for very wide, because it is exponential minus beta a, and it never goes, it goes to 0 at infinity. But if you can create an infinite square well kind of situation, then yes, there is no tunneling, but in reality there is no infinite square well. So there will be definitely tunneling, but if it is negligible, how does it matter to the experiment? So if you are not bothered about tunneling effect, your system does not require to be considered, then you don't consider. That's the thing happening. Yeah. So if it is negligible, you don't consider.
And just another request for a good book on this topic, to mention the name of one of good books.
Okay, so definitely I can give one book in BEC, one book in optical lattice. There are very good books, unlike the first talk, because first talk was in different directions. So I have to look at which review article is fit better. But in this second talk, I don't think any problem. I just can send you right away. So I'll send you all the references. Okay, then later on maybe you can convey to the students.
Okay, yeah. Once we get it from you, we will circulate it among the participants who have attended this lecture today. And there's just, and it's a bit off that Diponjit asked for also a good book on statistical mechanics. I don't know. If you want to answer it or not, yeah.
Go for Patria. Okay.
Go for Patria. Yeah. Okay.
It's a very good book. There's no alternative.
Okay, so thank you all for your patience, and thank you, Dr. Roy, for this wonderful lecture and the question answer session. You have answered many questions. So now I request Dr. Gayatri Pal to deliver the formal vote of thanks. Gayatri Di.
Can you, am I audible?
Yes.
Good evening, everyone. On behalf of the organizing committee of this webinar on quantum optics and quantum information, from fundamentals to application, I would like to propose the vote of thanks. First of all, I would like to express our gratitude to the resource person of the webinar, Dr. Utpal Roy, for delivering 2 illuminating lectures on quantum optics and information. His lucid and illustrative presentation in the first lecture gave us glimpses of some topics in basic quantum mechanics. The second part of his talk was equally informative, dealing with application of quantum concepts like the Bose-Einstein condensation, optical lattice, negative temperature, quantum sensors. Both the lectures were immensely appreciated by the participants. Thank you, Dr. Roy, for these interesting presentations. I would like to thank next our Principal Madam, Dr. Nivedita Chakraborty, for her encouragement and support for organizing this webinar and also for delivering the welcome address today. We acknowledge the keen interest shown by the participants, faculty members, and students from different colleges, institutions, and universities for attending this webinar and thank you all for your active participation today. I would like to thank Mr. Biplav Boshu of Ion Infotech for providing the technical support in this webinar today. My thanks are also towards Dr. Shinjini Dasgupta, who conducted the interactive session on Google Meet, and also to Ms. Kathakali Bishas, who managed the YouTube live screening and conducted the interactive sessions there efficiently. I would like to thank the conveners of this webinar, Dr. Shinjini Dasgupta and Dr. Shubhendu Chandra, and also all the members of the organizing committee for the effort they have put in to make this webinar a successful one. Thank you, everyone.
Thank you so much. It was so nice discussing with students and very nice. The time just passed like anything. Okay, thank you so much.
I think, can we take a photograph, Shinjini? Maybe if the participants
maybe.
present.
Yeah. If you guys,
yes.
Yeah, then we can take a group photo. Yeah.
We can take a group photo. Please switch on your cameras for the time.
Okay. Anyway, thank you, Gayatri, for delivering the vote of thanks, and we're also thankful to all the participants. And lots of questions actually proves that they liked it. Okay, and hopefully all of you have filled the feedback form. So after a few hours, we'll be closing to take the responses of the feedback form, and you will get your participation certificate within few days. Okay. So participants, requesting you to please turn on your camera.